day of this workshop on new connections in number theory and physics. We are quite happy at the overwhelming success of the breakout rooms, and so we have decided to keep them open every day of the conference. So there will be a discussion session today after the third talk, just like the other 2 days, and we will also do the same on Thursday and on Friday, so that everyone knows this. So the talks are recorded, and I have to remind you that when you ask questions, we welcome people to ask questions during the talks. You can just unmute yourself and ask a question, and this will be recorded. So unless you want to be recorded, then you can of course pose a question in the chat. There will also be a live transcript. So at the bottom, you can see a live transcript button. And if you need that, you can click it. Or if it's on and you prefer not to have it, you can unclick the live transcript. Okay, so then it's time to start the first talk of the day. I'm happy to introduce Jeff Harvey from University of Chicago, who will give a Blackboard talk. This is the first Blackboard talk of the conference. This will be about superconformal symmetry and quantum error correction. So please, Jeff, go ahead.
Okay, thank you very much. So I'd like to thank the organizers for the invitation to speak here. I'm going to be talking about some work that I did with Greg Moore in this paper, now published in JHEP. And unlike some of the speakers the other day, I don't have small children running around. I don't have cicadas in the background, but I do have to teach a large number of undergraduates about the fine and hyperfine structure of hydrogen a little bit later today. So I'm not going to be in the discussion section at the start, but I can be there for about the last 15 or 20 minutes, depending on how quickly I can get rid of my undergraduates. So if you have questions that aren't answered during the talk, feel free to ask questions. I will be available in the discussion section then. And of course, you can ask Greg, since he was my collaborator. So this paper was inspired by a couple of things. One was Matthew Moonshine, discovered now 11 years ago by Eguchi, Oguri, and Tachikawa that there is some sign of the Matthew group M24 in the elliptic genus of K3 surfaces. And it's kind of embarrassing that we still don't really understand why. And so we wanted to understand this. And then we were very directly motivated by a really nice paper by Gabardine, Taormina, Volpato, and Wendland, who looked at a particular superconformal field theory that corresponds to a K3 sigma model and that has a very large symmetry group that preserves the 4,4 superconformal symmetry. And in this paper, they said things like the basis of Ramon states corresponds to something called the miracle octet generator, which is a device, mathematical device that's used to construct the Golay code. And so we wanted to know, what is the MOG doing in K3? And more generally, I'll say a little bit about what the MOG is, but it's a way of constructing the Golay code. And the automorphism group of the Golay code is M24. So although in their paper, they identified certain subgroups of M24 as preserving the superconformal symmetry and used that to establish this group, we were hoping that maybe if we could understand at a deeper level what was going on here, that we would get an important clue of how to find M24. So we didn't succeed in doing that, but we did find some other things which I think are interesting, which I'm going to try to explain to you, although I'm not going to explain everything in our paper because there's a lot of technical detail. So I wanted to say before explaining some of the detail that moonshine, which is really the topic here, includes both general principles and very specific models. So I would say the general organizing principle that has been most useful is the role played by genus 0 subgroups of SL2R. These, in monstrous moonshine, organize the Mackay-Thompson series, which are kind of character-valued versions of the partition function. They classify the various kinds of umbral moonshine, as was shown in a paper by Cheng and Duncan. And they also, in some work that will hopefully appear one of these days with that I'm doing with John Duncan and Brandon Rehun, they also classify another set of moonshines, of which moonshine for the Thompson group is one example. So there's some general organizing principles, but of course, there's also a great deal of work that has to do with very specific detailed models. And here the sort of ultimate example is the two-dimensional conformal field theory or holomorphic vertex operator V natural constructed by Frankel, Lepowski, and Merman, which is the space in which monstrous moonshine lives and acts. So this particular K3 superconformal field theory, which was not first written down by these people, but since they did such a nice job of studying it, I'll refer to it as the GTVW K3, is, well, it doesn't explain M24, but it's somehow like this V natural of FLM, in that it's a very detailed, rich structure with a large symmetry group and a very intricate structure. And we've uncovered some new features of the intricate structure in that model. So the general lesson that that we will try to extract from this is that there is a new connection in this model and in others between the construction of superconformal symmetry and quantum error correction. I should say for the kind of VOA people in the audience, if there are some, that of course classical error correction plays a very important role in many constructions in vertex operator algebras, and plays a very, for example, an important role in constructing special lattices, which play a role in lattice VOAs. But I think the appearance of quantum error correction in conformal field theory is a new aspect. So lecturing at the blackboard has the advantage that I can't go too fast. It has the disadvantage that I can't cover very much. And I'm a little afraid that I might run out of time, but we'll see how it goes. Okay, so my plan is to quickly say a little bit about some of the codes and error correction that appear in this particular conformal field theory. So I'm going to start by talking a little bit about classical error correction. Which will allow me to introduce some of the ingredients. I'll then move on to talk about quantum error correction very briefly, and then I'll try to show you how some of the structures that I've discussed in talking about error correction are manifested in this particular theory. So in classical error correction, one usually starts with some prime power and the field FQ associated to that prime power. And then you imagine a message which consists of elements of that field. So we might have some long message with each one of these elements being in the field. And if we have a long message, it's often convenient to break that up into words. So we'll imagine that we have words of length k, which I have broken this message up into. And what we want to do is we want to encode this into a bigger space in a way that will allow us to detect and correct errors. So what we're going to do is we're going to encode this in a set of words with n greater than k. And in the particular case that we're going to be looking at, we are going to be considering linear codes. So for a linear code, there is a code word which is in FQ to the n, and that code word is our message word times a n by k matrix G. So this is our message, and we encode it linearly in a bigger space. And this matrix G can be written in a canonical form as just an identity matrix and then another matrix. So essentially the first k digits of G are the message, and then they get encoded in some way. We'll refer to this as an NK code and sometimes as an NKD code, where D is known as the Hamming distance, and it's the minimum over all words in the code subspace, which is the subspace spanned by all the code words, of the distance between two code words. And this distance is the number of digits where C1 and C2 differ. So to save time, I have written down a few details of some examples here. So in particular, up here, I have written the generating matrix of the 743 Hamming code. So this takes this is a code where Q is equal to 2. We're working over field with 2 elements. We have 4-bit words that we encode into 7-bit code words. And the feature that is important about this code is that the Hamming distance is 3. And this 3 implies that if you have a 1-bit error, that gives you a word with distance 1 from a code word, since you've just changed 1 bit. But because the next code word has distance 3 from the word that you started with, there is always a unique code word that is closest to the word with 1 error in it. So that allows you to correct any 1-bit error by simply finding the closest code word to the word with the error in it. Now, I mention the Hamming code because it's related to 2 other codes that play an important role in CFTs and in this model. So first of all, there is an 8-4, I guess, binary Hamming code, or extended Hamming code, that you get by adding a parity bit. And there's a well-known relationship between this extension of the Hamming code and the E8 lattice, where the Hamming distance of the code translates into the sphere packing properties of the E8 lattice. And there's also another code called a 6-4 code, where you drop the 7th digit. And this code is going to reappear in this K3 signal model. And I've written down the 16 code words in that in a notation to the left there, where we list the entries with a 1. So for example, this entry here with 235 means it's 0, 1, 1, 0, 1, 0. There's also a code which is going to play a role here called the hexacode. And the hexacode involves a field over a field of order of characteristic 2 and order 4, which is something that physicists don't usually encounter. Physicists, I think, tend to think that all fields are ZP with P a prime, but okay, they're not. And the hexacode is based on the field F4 with 4 elements here, and has a generating matrix, which I've listed here. And here I've written down the addition and multiplication rules if you want. They're also in our paper, but just as a reference. Why is the hexacode important? Well, for us, it's important because it plays a crucial role in a construction of a larger code called the Golay code. And that appears in this particular K3 signal model. So I think it's difficult to give all the details, but I'll just say that there is an extended binary Golay code which takes 12-bit words, embeds them in 24-bit code words, and can correct any 3-bit errors. It was also used in various missions like the Voyager 1 and 2 missions to transfer data. The MOG is a way of constructing this code subspace. So this is there's a code subspace, which is a 2 to the 12th dimensional subspace of F2 to the 24. And you can actually construct it by hand using the MOG, which is kind of an astounding fact. And the book, the Sphere Packings, Lattices, and Groups book, gives you practice in doing this with some exercises. But the basic element of the MOG is that you take an element of F4 and an element of F2, a plus or minus if you want, and then you construct certain maps which take an element of F4 and F2 and produce an element in F2 to the 4th. And then there's an extension of this, which takes 6 copies of this into F2 to the 24th. And if you think of an element here as a list of elements in F4 and F2, then whenever X1 to X6 are in the hexacode, which is the code defined up here by this matrix G, and whenever the sum of the epsilons is 0 mod 1, mod 2, then this is in the Golay code. Or rather, it's in the even Golay code. And then there's a version of this that involves G minus and F minus, which adds the odd elements. So I'm not going through the details, obviously, but this little picture over here kind of gives you an example. It takes an element of the hexacode, and then according to these plus or minus signs, you associate to that elements of F2 to the 4th, and then you do that 6 times, and you get a 6x4 array of zeros and ones, and this encoding tells you that this will be an element of the Golay code. And the hexacode is small enough and simple enough that you can learn to recognize its code words kind of by hand, by looking at them. And then this encoding tells you how to construct all elements of the Golay code. Okay, so that's my extremely quick review of classical error correction and certain error correcting codes that are going to reappear in the context of a K3 sigma model. So my next task is to say a few words about quantum error correction. And in quantum error correction, we typically deal with Q bits, although we could deal with Q trits or higher, versions of qubits. But for our purposes, a qubit is simply a state in a two-dimensional complex vector space. So I'm using 0 and 1 as an orthonormal basis of our complex vector space. And in quantum mechanics, you either normalize your states or the overall norm doesn't matter. So strictly speaking, if we think of this state psi of this form, then psi is really an element of CP1. Now, in trying to formulate quantum computation, you have the problem that there's all sorts of noise, and it's very hard to maintain quantum coherence in quantum mechanical states. So the environment, cosmic rays, whatever, can sometimes act on these bits, either to flip them or maybe change their phase, or in general, do some kind of unitary transformation that destroys the information. And we're used to the idea in quantum mechanics that if you try to measure an observable, that you destroy information. So for example, you might try to measure the observable, which is the projection operator onto the state 0. And of course, if you get 0 for this measurement, then you know you're in the state 1. And if you get 1, then you know you're in the state 0. And after the measurement, this is the state or this is the state. And the information in A and B, which is picking out a point in the block sphere, is destroyed by the measurement. So it seems difficult, but you can use entanglement to solve the problem of how you can encode quantum information in a way that you can detect and correct errors. And I think the simplest example of this is to take this 1 qubit state and embed it into a state with 3 qubits, so in the tensor product of C2 with itself 3 times. And now, if you have a 1 qubit flip error, let's say, just for example, so a bit flip error is an error that takes a single 0 to a 1 or a single 1 to a 0. If that happens to this state, you can make a measurement to figure out what happened, and then you can do a unitary transformation to restore the information in the original state. And the way you do this is you measure a set of commuting operators. So there's a projection operator, and if you get 1 for this projection operator, then you know that there was no error. Then there's another projection operator, and if you measure 1 for this projection operator, then you know that the error was in the first bit. And similarly, there's 1 for the second bit and 1 for the third bit, where the second entry or the third entry is this distinguished element of this list. So these are 4 commuting projection operators. They can be measured simultaneously, and their eigenvalues tell you where the error occurred. And once you know where the error occurred is, then there's clearly a unitary transformation that just flips that bit back. So particular kinds of errors, bit flip errors that just change a 0 to a 1 or vice versa, can be detected and corrected in this way. And the basic idea is that you have this 8-dimensional space, and you have arranged things so that when there is just one error, it takes the state into an orthogonal space, and there are projection operators onto orthogonal subspaces that can measure where that state that's orthogonal to the state you started with is. And that's possible because you're now working in a higher dimensional space. So this is an example of how you correct a particular quantum error, but there are other kinds of quantum errors that you can consider, and you want in general to be able to detect and correct those if you're going to implement quantum computation. So my general understanding of the state of quantum computation right now is that while you can build quantum computers with increasing number of qubits, really effective quantum computation is going to require error correction. And so orders of magnitude more qubits than are currently used in order to actually implement this error correction. So there's a general formulation of what quantum error correction is that you can find discussed in John Preskel's notes or the book by Nielsen and Chang or in other places. So if we have the Hilbert space of n qubits, a quantum error correcting code is a Hilbert subspace C along with a set E of error operators that catalog the kinds of errors that you want to try to correct, and that satisfy that if EI and EJ are in the set E, then if P is the projection operator onto C, this code subspace, and EI and EJ are error operators, that there is a Hermitian matrix, alpha ij, such that the errors obey this. So this is kind of related to projecting onto the subspace, acting with an error, and then taking the inner product of that and showing that it, up to this Hermitian matrix, projects onto the subspace. Now, I'm not going to go through the details of how you detect or correct the errors given this condition, but it's explained in the references that I gave you. For us, the possible errors are going to be tensor products of what are known as Pauli operators in the quantum computation world. That is, they're going to be combinations of xy, zi acting on the ith component of our tensor product space, where these are just the usual Pauli matrices, but now written with capital letters because that's the notation that the quantum computation people like. So for example, on, I don't know, C2 to the fifth, we might have something like xy, the identity, zx. That would be an example of a possible error operator that could act on states in this space. And there is also a notion here. So when we have C2 to the n, and when our code subspace has dimension 2 to the k, where k is clearly less than n, then we call this an nk code, but we put it in double square brackets in order to indicate that it is a quantum code rather than a classical code. So there's one more notion that we need, and that is an analog of the Hamming distance for quantum error correction. The Hamming distance for classical codes tells you how many errors you can detect and correct, and there's an analog of that for quantum error correction. Namely, D is defined to be the minimum weight of the error operators in your set of error operators for those operators that are not the identity on your code subspace, and where the weight of E is the number of slots that don't have the identity operator, that have an X, Y, or Z. So I'm going to be talking about, specific things here, and the specific thing here is a code that is a 513 code. So that means the code subspace C is a one-dimensional subspace of, or well, two complex dimensional subspace of C2 to the fifth. So this code is the smallest code that corrects any one qubit Pauli error. And there are various ways of constructing these quantum error corrected codes. This particular one is constructed as a stabilizer code. So for this code, the code subspace is the subspace stabilized by a group S, and the group S can be defined by its generators, which are a set of unitary operators. So I'm not writing down these because I don't think you possibly remember them, and the details don't matter so much. But there is a particular two complex dimensional subspace, which is stabilized by these, and its elements can be written as a sum over group elements of the group element acting on the state 0 to the 6th, and then this rather simple operator acting on 0 bar. So these two states are a basis of the code subspace. And with some work, you can show that what I claimed is true, that there are a set of measurements of projection operators that you can make that will allow you to detect and then correct any error induced by the action of X, Y, or Z in any one of the slots of the bit. And then finally, there is one kind of not quantum error correcting, but nonetheless interesting state that you can make by adding one more auxiliary state. And that is in C2 to the 6th, you can create a state which just takes your auxiliary bit and entangles it, if you want, with the state in this code. Now, this state is a rather special state, and I learned of one of its special properties in the notes by John Preskill. It's a kind of higher dimensional version of the maximally entangled states that play a role in, Bell's theorem and the EPR paradox, in that if you take the density matrix, which you get by tracing over any 3 of the 6 qubits, so tracing over half of the qubits, you get a totally random state that is proportional to the identity matrix. This is an extremely non-trivial fact and shows that this state is special and somehow a kind of higher dimensional version of a maximally entangled state. Okay, so I've used more than half of my time, and I haven't said anything about physics or K3, but I've talked about some weird math. Well, excuse the weird, but anyway, some math involving the MOG construction of the Golay code and some very special quantum error correction, which is special in the sense that it's the smallest code that allows you to detect and correct one quantum error, just like the Hamming code up here is the smallest classical code that allows you to detect and correct one error. And then a state that's closely related to that lives in this complex vector space. So my goal in the rest of the talk is to briefly, obviously, explain where these ingredients arise in this particular K3 sigma model of GTVW. So I need to take a drink of water, and maybe it's a good time to just ask if there are any questions before I move on to the next part of the talk. Okay. So now we need to talk about this particular K3 superconformal field theory. Its main ingredient is that it is constructed out of 6 copies of affine SU2 at level 1. And there are 2 highest weight representations of level 1 SU2 that have conformal weights 0 or 1/4, and where the lowest states are either a singlet or a doublet of the global SU2 part of the affine SU2 symmetry. And the fusion rules of these 2 highest weight representations are isomorphic to F2. So you can see that we have 6 copies of something that has a kind of Z2 or F2 label. So you start to see some possible connections to the codes. The Hilbert space of this conformal field theory can be decomposed into holomorphic and anti-holomorphic parts. We're not doing holomorphic VOAs, but rather conformal field theories with both holomorphic and anti-holomorphic parts. And these labels live in a set S, where S and S bar are labeled by elements of F2 to the 6th that label which representations occur, and the components S alpha are the same on the left and right up to a universal part X, which can either be 0 or 1. This gives you a spectrum that is not completely local. It's rather non-local by the fact that it includes half integer dimension fields, which you need in order to define the superconformal generators. So this model has n equals 4 superconformal symmetry. And there are presentations of it that make this obvious. So for example, it has a presentation where you start with a 4-dimensional torus at the enhanced symmetry point in string theory, where it gives you affine D4 at level 1. And then you do a Z2 orbifold of that. So it's a kind of special Kummer surface construction. And that is well known to have n equals 4 superconformal symmetry. But in the presentation I've given in terms of 6 copies of affine SU2 at level 1, it's far from obvious that it has n equals 4 superconformal symmetry. So in particular, it has 4 holomorphic dimension 3/2 0 fields, and it has 4 anti-holomorphic dimension 0 3/2 fields. And what I want to explain is that the construction in this language of the superconformal symmetry of this model proceeds via quantum error correction. So to do that, let's note that each SU2 factor has 2 dimension 1/4 primaries, the 2 primaries that create the 2 states in a doublet of SU2. And therefore, you can make a holomorphic dimension 3/2 field by taking a product of 6 of these labeled by a plus or minus 1, where the plus or minus 1 is labeling which of the two dimension 1/4 fields you're talking about. So in other words, there are 2 to the 6th possible dimension 3/2 fields.
Sorry, quick question. Is it possible to say where these 6 SU2s are in that D4 presentation?
Sort of, if I can recall. So D4 is SO8, which contains SO4 times SO4, which contains, which is the same as SU2 to the 4th. But this is a super version of D4. There are also fermion fields, and the fermion fields, I believe, to give you another SO4, and I think so altogether you get SU2 to the 6th from doing this kind of decomposition. Maybe one of GTVW, if they're in the audience, can correct me if I just said something wrong, but I think that's how it works. So this means that we can associate a dimension 3/2 operator to a state in the 6-qubit Hilbert space. Or if we're given a state in this space, which is some linear combination, we can associate to that a dimension 3/2 operator. So now what we're going to do is we're going to translate properties that we want our dimension 3/2 operator to have into properties of the state viewed as a state in the 6-qubit Hilbert space. So the main property that we have to demand of this operator is that it gives rise to the n=4 superconformal algebra involving SU2 currents and the stress energy tensor. So that is encoded in the OPE, and so the OPE of 2 of these operators of dimension 3/2, well, I'm actually doing the same one because we're just going to focus on that for the moment. This takes the form S bar S over Z12 cubed plus a term that involves S bar S over Z12 times the stress energy tensor, plus a term with some constant, which we don't care about, which involves S bar sigma ABS JAJB over Z12. And here sigma A is a kind of multi-label for the ith Pauli matrix occurring in the alpha slot. And sigma AB is the usual commutator. Now, this term is not supposed to appear in the OPE. It's not consistent with even n=1 superconformal symmetry. So we have to require that S bar sigma ABS is equal to 0. But if we translate that back into properties of states in this 6-dimensional complex Hilbert space, this is the quantum error correcting property. It says that the error where it says that distinct distinct errors give orthogonal states. Because this is the inner product of an error associated with the label B with a error acting on a state associated with the label A. So in order to detect and correct the states, this orthogonality property is required, and that is precisely this vanishing condition on this coefficient in the OPE. And in fact, you can write down very explicitly what the state is that corresponds to the different superconformal generators.
Jeff, you have 10 minutes.
Thanks. So the state that corresponds to n equals one superconformal generator can be written explicitly as a quarter sum over words in the hexacode times h of w times the state 0 to the 6th. And h of w is something that is defined up here. So in this theory, we have SU2 to the 6th, and SU2 has a subgroup of called the quaternion group, which consists of the identity and then plus or minus I times the 3 Pauli matrices. There is a homomorphism from the quaternion group to the field, well, not the field F4, but rather F4 as an abelian group, which is just Z2 times Z2. And H is a section of this given by the formula here, which tells you how each element of F4 plus maps to an element of the quaternion group. So you take that element here for each, well, you extend it to F4 to the 6th in the obvious way, and then you act on the state 0 to the 6th, and that is the state that corresponds to to an n equals 1 superconformal symmetry. And it's non-trivial that this state is a unitary operator times this maximally entangled state that I talked about earlier in quantum error correction. And we thank Tom Monero for a computation that determined explicitly that this was true and found the unitary operator. So the upshot of this is that, well, first of all, you can extend it to n equals 4, slightly more complicated versions, but still involving properties of quantum error correction, give you all 4. But if you just pick one, then there's a very beautiful connection between the properties of this n equals 1 superconformal generator and this special state that occurs in the theory of quantum error correction. There are a number of other things in our paper. I guess I'll try to mention one of them briefly, but then I'll definitely be out of time. I guess one thing I should mention before I completely out of time is that one can ask whether this kind of connection between superconformal symmetry and quantum error correction extends to other models. And we do an analysis for the theory that has moonshine for the Conway group that John Duncan has investigated and show that it's true there. And there's an interesting list of holomorphic VOAs that Theo Johnson Freyd has investigated. And it would be interesting to look there. So the final thing
excuse me, Jeff?
Yes.
Yeah. When you make this statement about the unitary operator, I assume you're saying something special about the unitary operator. Otherwise, this seems to be a, why does this statement have some content?
It's a local unitary operator. It's a product of unitary operators at each of the 6 factors.
Ah, okay, so I see.
Yeah, yeah. I guess I was assuming that.
But transformation in
Yeah, so I mean, it preserves the maximal entanglement of the state.
I see. Okay, thanks.
Jeff, you skipped over the pink lemmas. Was that intentional?
I can't really hear you, Greg. Greg?
You skipped over the pink lemmas. Was that intentional?
I only have so much time.
Okay. But there, okay.
Yeah, I'm skipping over a lot of things. Anyway, yeah, so let me just mention one last thing. Because I started out in the motivation saying that M24 is the automorphism group of the Golay code. So it seems like if we could understand the Golay code, we ought to be able to understand Matthew Moonshine. And we failed, but we failed in an interesting way. And maybe the interesting way that we failed will suggest something to someone else. So there is the six copies of the quaternion group that we get by embedding the quaternion group into SU2. And let's consider an n equals 1 holomorphic superconformal generator of dimension 3 halves 0, and an anti-holomorphic one of dimension 0 3/2. So in other words, we're going to look at 1-1 superconformal symmetry. And then we're further going to look at a parity transformation that interchanges the SU2s on the left and right and interchanges psi left and psi right. And although I'm not going to give you the details, you can extend the quaternion group to include this parity transformation. And you can ask what the stabilizer is in this extension of the quaternion group of an n equals 1 supercharge, which is psi left minus psi right. So that defines a certain group. This group acts on the space of Ramond ground states of this sigma model. And the space of Ramond ground states in this model is the space of dimension 1/4 operators, and it's just a 24-dimensional space, which is a 2, under SU2 left times SU2 right, labeled by the 6 SU2 elements. So this you can think of as very similar to the MOG, where the 24 ground states are labeled by a row and a column, where the column tells you which SU2 and the row tells you which one of the 4 states. So there is a representation that you get of this group that stabilizes an n equals 1 non-chiral superconformal symmetry within this extension of the quaternion group. And this is the Golay code. So we found M24 in the GTVW K3 sigma model. It's the automorphism group of the representation of this stabilizer group that you get acting on the Ramond ground states. And when we first discovered this, we were running around Aspen, jumping up and down with joy, because we figured if we found the Golay code, we had to have explained M24 moonshine. But a couple days later, we were walking around with despair because we couldn't see how to connect this Golay code to the way that it occurs in Matthew Moonshine, where it acts on the n equals 4 superconformal decomposition of the elliptic genus. And this doesn't seem to, this is a symmetry group it's an automorphism group of a symmetry group. And we were not able to see a connection between the M24, that's the automorphism group of the group defined this way, and the Matthew moonshine phenomenon. But maybe someone in this audience is smarter than we are, and we'll figure out that there is some connection. But in any event, there are a number of other things that we did in our paper, which I haven't talked about and I think are interesting. I've tried to focus on a couple of elements. It's an incredibly rich, intricate theory with really cool connections to both classical codes and quantum error correcting codes. And there's perhaps more to the story, but that's all I know for now and all I have time for. So I'll stop.
Thanks a lot, Greg, Jeff, for that beautiful talk. So let's applause. Yeah, so we are right on time. So I would suggest that we postpone questions for Jeff until the discussion session. Now, I remind you that Jeff will not be there for the first part, and then at some point he will pop in and probably also be present tomorrow, right? If you want to ask.
Yeah, I'd be happy to, yeah, like the last 20 minutes today and in the discussion section tomorrow, I'd be happy to answer questions.
Okay, perfect. Thank you very much. And then maybe Greg can share. Yes, perfect.
I forgot that I have to unmute before I can share.
Ah,
They don't commute.
they don't commute.
Okay. How's that? Can you see it?
That looks good. So we just need, yes, perfect. So then we welcome Greg Moore from Rutgers. We're very happy to have you. And you will talk about n=2 star super Young-Mills and four-manifold invariants. But the mock modular forms have disappeared, or?
They'll appear.
Okay.
I guess they disappeared from the title.
Yes.
Okay. Well, thanks, Daniel, and the other organizers for the invitation to speak here. So the title of the talk is n=2 star super Young-Mills and four-manifold invariants. So let's see, how can I get rid of this annoying Zoom message about transcripts? There we go. Okay. So yes. So this is a talk that a version of a talk that I've given at the KITP last December and also at the Institute for Advanced Study in March. So if you've seen those talks, you don't want to hear it again. All right, let's start again here. So this is work that I've been doing over the past few years with Jan Manscott, and we finally got our paper out. And it's closely related to previous work from the late 1990s. And very interestingly, it's also related to recent work of mathematicians, Gocha, Kuhl, Nakajima, and Williams. And I'll come back to that at the end of the talk. So here is the outline of the talk. I'll begin with some geometric motivation, then give you a little bit of geometric background, and then I'll talk about the physical formulation of the four-manifold invariants in question, then the mathematical formulation of the four-manifold invariants in question, and then we'll come to the topic that might be of interest to members of this conference, the Coulomb branch integral, and finally end up with some very explicit results. So let's begin by remembering the glorious history of super Yang-Mills and four-manifolds, which begins with the discovery of instantons in 1975, and then in the hands of the Oxford School that led to the introduction of Donaldson invariants in 1982. And then Atiyah asked Witten the important question, what is the physical interpretation of the Donaldson invariants? And Witten's answer was to invent topological quantum field theory. And then the desire to evaluate Donaldson invariants via topological quantum field theory was at least one of the motivations for the Seiberg-Witten discoveries and led to the introduction of Seiberg-Witten invariants in the mid-90s. which led to the revolution of 1995. And here I'm not talking about the string revolution of 1995. I'm talking about the revolution in four-manifold theory of 1995, which was so dramatic that it left many physicists with the impression that the physicists had solved all problems in four-manifold theory. But that's far from the case. Not all questions are answered. And so more than 10 years after the Seiberg-Witten invariants were introduced, important mathematicians wrote papers with titles like this one that you see. Now, the Seiberg-Witten revolution was based on pure n equals 2 super Yang-Mills theory. And the basic idea of topological twisting applies to any four-dimensional n equals 2 quantum field theory. So it's a natural question to ask, is there more to learn about four-manifold invariants from supersymmetric quantum field theory? After all, there are these many open problems. I'm not going to mention any of them, but there are many open problems in the differential topology of four-manifolds. Physics has been wildly successful in the past. There's lots of other quantum field theories out there that might help with some of those questions. So that's for me one of the motivations. Now in this talk we won't be introducing new four-manifold invariants, but we will be studying a very interesting example of these invariants associated with another quantum field theory, the so-called n equals 2 star theory. And as I'll show you, it interpolates between the Donaldson and the Vafa-Witten invariants. And although it doesn't introduce new four-manifold invariants, as we've learned some important lessons for the generalization of the story to other n equals 2 theories along the way, as I'll mention throughout the talk. Now, a key to the explicit evaluation of these invariants is the so-called Coulomb branch integral, also known as the U-plane integral, which involves automorphic forms, indefinite theta functions, Mach modular forms, and Jacobi mass forms, which is why I'm talking about it at this conference. Okay, so let's begin with a few geometrical preliminaries. So the four-manifold invariants we consider will be smooth, compact, oriented, without boundary. For simplicity, they'll be simply connected. And we will assume, as in Donaldson theory, that our four-manifold admits an almost complex structure, which is a mild constraint. It just means that B2 plus is odd. B2 plus is the dimension of the space of self-dual two forms, self-dual closed, self-dual two-dimensional cohomology classes, or if you prefer, in the second homology, there's an intersection product. It's the dimension, the maximal dimension of the positive subspace. And importantly, we do not assume that X is spin. Let me remind you what an almost complex structure is. The complexified cotangent bundle of our four-manifold has a basis of EI and EI star. I goes from 1 to 2. And across patches, the EIs rotate by unitary transformations, so that if you use the standard homomorphism from U2 into SO4, you get the transition functions of the oriented cotangent bundle of X. We also need to know what a spin C structure is. So here is a definition of the group spin C of 4. It's pairs of 2 by 2 unitary matrix of equal determinant. And there's a homomorphism, pi, from spin C of 4 to SO4, where we conjugate quaternions in the usual way. And so to give a spin C structure is to give transition functions for a spin C4 bundle, so that if I apply this homomorphism, I get the SO4 transition functions of the oriented cotangent bundle of X. So here again is the definition of spin C of 4. It has two obvious two-dimensional representations by taking the fundamental representation of each of the two U2 factors. So then if I have a spin C structure, there's an associated bundle. These will be called chiral spinor bundles. So these are the analogs of spinors on a non-spin manifold. You have to give a spin C structure, then you have spinors. And I'll call them W plus and W minus. Those are rank 2 vector bundles, so their determinant is now a line bundle. That line bundle has a first Chern class in H2 of XZ, and I'll call that the characteristic class of the spin C structure. So now a very important invariant is the following. You can prove that C squared minus twice the Euler character minus 3 times the signature divided by 8 is an integer. That's an important integer, which I'll call L, and we'll see L throughout the talk. So an almost complex structure, J, defines a canonical spin C structure, S of J, and that'll also be used later in the talk. So the way that goes is that there's a nice homomorphism from U2 into spin C of 4, I wrote it out there, and it has the property that if I compose it with pi to get into SO4, that's conjugate to the standard embedding of U2 into SO4, and so that way an almost complex structure defines a canonical spin C structure, and for this canonical spin C structure, this invariant L is 0. So to shorten the words, I'll just call it the canonical spin C structure later on. And that always means that you're assuming some particular almost complex structure. All right. Now let's talk about the physical formulation of the partition function. So for a physicist, we're talking about what's called SU2 n equals 2 star theory. And briefly what that means is the following. There's a super Poincare algebra. It's a super Lie algebra, and its bosonic part has, as a Lie algebra, the SU2 plus SU2 minus local Lorentz symmetry, and then a global symmetry known as SU2R symmetry, and of course the gauge symmetry. Hypermultiplet scalars then are in a quaternionic representation of the gauge group. We take the adjoint representation of the gauge group, that's what makes it n equals 2 star, and it's a quaternionic representation, so we tensor product with the quaternions. The unit quaternions act on the right, and that's the SU2R symmetry. So if we think in terms of complex scalar fields, we have a doublet of complex scalar fields, and that's important for topological twisting. In topological twisting, we couple to a background SU2R gauge field, and we identify SU2R with SU2 plus in the local Lorentz algebra. So that means that under topological twisting, the hypermultiplet scalar fields become spinners under the twisting. What if X is not spin? Well, I just told you what to do. You cure the problem by introducing an ultraviolet spin C structure. I'll call it S of UV. And then, with an ultraviolet spin C structure, the hypermultiplet scalars are in the n equals 2 star theory are spinners in W plus. Now for n equals 2 star, we learn an important lesson here. So the basic topological twisting of Witten needs to be supplemented with extra data. You need to introduce this ultraviolet spin C structure, and answers very much depend on that spin C structure. So the basic idea of topological twisting is not enough. And as far as I know, it's actually not known how to topologically twist the general 4-dimensional n equals 2 theory. For Lagrangian class S theories, I know what to do, but for non-Lagrangian ones, I do not know what to do. But it's an interesting open problem. Anyway, returning to n equals 2 star, now let's talk about the topologically twisted partition function. So what are the data we need to formulate the partition function? Well, first of all, we need a complexified coupling in the upper half plane. I'll call it tau uv for mathematicians. Just think of it as a point in the upper half plane, and the associated Q parameter is defined there. Now, we also introduce a mass parameter, and it's not usually said, but there's actually an ultraviolet scale in this theory, and the topological quantities only depend on the ratio of m over lambda. As I've just stressed, we also have to introduce a spin C structure for the topological theory, and finally, for our partition function, we have what's called an 't flux, which is a degree 2 cohomology class with coefficients in Z2. Now, of course, these are the data, but of course, to write a path integral and a Lagrangian, we also have to introduce a metric. However, because of topological twisting, the response to the metric, which is the energy momentum tensor, is Q exact, and so a formal argument says that the metric dependence of the partition function should therefore drop out. In support of that conjecture, the action can be written this way as tau uv times the trace of f wedge f plus q exact stuff. So you see there's no metric in that action if you modulo q exact. And it's also holomorphic in tau uv. And so formally, we expect the partition function to be holomorphic in tau uv and metric independent. That is indeed true for B2 plus bigger than 1. However, for B2 plus equals 1, there are holomorphic and metric anomalies, which we'll talk about later. This theory also has operators. The Q cohomology in the operator content depends on the homology of the four-manifold. So for us, we'll only look at degree 0 homology and degree 2 homology. So the points are going to be sums of, the 0 degree homology class P is a sum of points with integer coefficients, and the second degree homology will be denoted S. And so associated with those, we have an operator at points and an operator where we integrate over S. So all in all, the path integral then defines a function that depends on those four data, nu, tau uv, cuv, and t, and it's a function on the homology of the four-manifold valued in the complex numbers. And here's the physics definition. If I'm given a homology class x, I have an operator e to the o of x. I take its path integral, and that's in principle some number. So that's very abstract. What Jan and I did was evaluate this function very explicitly and then check some physical expectations. Okay, so let me come to the mathematical formulation of the partition function. So for what we begin with is a principal SO3 bundle, P over X. And we're talking about a theory of a connection, A, on that principal bundle, and what mathematicians call a monopole field. These are just the hypermultiplet scalars I was talking about before. Mathematically, the monopole field is a section of the chiral spin bundle, W plus, tensor the complexified adjoint bundle. And then there are equations of motion in this theory, and our path integral is going to localize to those equations of motion. They're sometimes called the Q fixed point equations, and these are the equations. So we have the Dirac equation for the monopole field, and then we have a deformation of the anti-self-dual instanton equation. I'll call those the adjoint Seiberg-Witten equations, or the non-abelian Seiberg-Witten equations, or the non-abelian monopole equations. So we have a moduli space of solutions to these equations here, and the moduli space has components, and they're labeled by the second Stiefel-Whitney class of P. That's what physicists call the 't Hooft flux, and the instanton number K. So here's the math definition of the partition function. So in blue, you have the physics definition, and in red, you have the math definition. So we sum over instanton sectors. We integrate over the moduli space. What we integrate is e to the mu of x, where mu is a map from the homology of x to the cohomology of the moduli space, times the Euler class of a certain bundle. It's the obstruction bundle for the elliptic complex associated with those adjoint Seiberg-Witten equations. It's actually an equivariant Euler class. I'll come to that in just a moment. Now, the way you get from the blue line to the red line is a formal argument based on this Q symmetry. So you can localize the infinite dimensional path integral to a finite dimensional integral over the moduli space of solutions to these differential equations. I should say something about this moduli space, or at least its virtual dimension, this MQK nu. So by index theory, you can calculate that the virtual dimension of this monopole moduli space is 2L. L is that integer I mentioned before, times the dimension of the gauge group, which is 3 for us. And the important thing to note here is that it's independent of the instanton number K. The way that works is that if you deform the instanton equation, you get 8K moduli, but then the index of the Dirac operator has minus 8K, so the K's cancel out. And that has an important consequence, that the correlation functions on the homology are infinite series in QUV, even when I don't insert any operators at all, when x is 0. When I look at the pure partition function, it's still an infinite series, and they will have interesting modular properties. Now, I mentioned equivariance before. Here again are the non-abelian monopole equations, and there's a clear symmetry. I rotate the monopole field by a constant scalar, by a constant phase, and that's clearly a symmetry of these equations. Now, therefore, this U1 acts on the moduli space, and we can try and localize with respect to this U1. And so then under this localization, we have equivariant cohomology of the moduli space, and that's where the Donaldson mu of x actually lives, and that's what corresponds to the physical operator O of x. And then T, the mass parameter, is the equivariant parameter. So here's what we get when we do U1 localization. We have to look at the fixed point set of this U1 action, and there are two branches. The first branch is where m equals 0, and then the equations manifestly become the anti-self-dual instanton equation. So inside of this moduli space m sub q is a copy of instanton moduli space. But then there's another branch where the monopole field is either upper triangular or lower triangular, because in that case, a phase rotation of m is gauge equivalent to itself. Okay, so the U1 localization takes an integral over the Q moduli space to the instanton moduli space plus the abelian branch. That's what I'm calling the other branch. And now I want to first focus on the instanton contribution. So here's the instanton contribution. The Euler class can be written out as a product over splitting classes, and then you can expand that in 1 over t. T is the mass parameter, but also the equivariant parameter. So now let's study the limits as t goes to 0 and infinity. So as t goes to infinity, that's taking the mass parameter to infinity. So physically, that's taking the n equals 2 star theory to the pure theory. As t goes to infinity, clearly the leading term in this 1 over t expansion here is the 0th Chern class of the obstruction bundle. That's just 1. So we have just e to the mu of x, and by definition, those are the Donaldson invariants. So we expect that the leading term as the mass goes to infinity should give us the Donaldson invariants. On the other hand, if t goes to 0, what's the leading term for m goes to 0? Then we clearly are picking off the top Chern class. And for the canonical spin C structure, the obstruction bundle is the cotangent bundle of moduli space. And so we should be getting the Euler character of instanton moduli space. Now, many people will not be surprised because they'll say, of course, as m goes to 0, the n equals 2 star theory becomes the n equals 4 super Yang-Mills theory, and we know about the Vafa-Witten theory. Indeed, the Vafa-Witten invariants compute the Euler character of instanton moduli space, and they are S-duality covariant. Our instanton contribution also computes the Euler character for the canonical spin C structure, and the mass goes to 0. And together with the abelian branch is S-duality covariant. So the natural guess is that we're going to get Vafa-Witten invariants. And in cases where we can compare, such as projective surfaces, that limit as t goes to 0 does indeed reproduce known results about the Vafa-Witten invariants. But I want to stress that this is a little surprising because the Donaldson-Witten and the Vafa-Witten twists are very different. And contrary to what I said in a talk last July, the Q fixed point equations are also different, but they can be viewed as deformation equivalent. And that's a long story that's in our paper that I went into in detail in my talk at the Institute in March, but I'm not going to go into here. All right, so now let's come to the Coulomb branch integral. Okay, so this is where we make some connections with the number theory. So to get there, we note that the partition function on a compact manifold will equal a sum over all the vacua. In particular, we need to integrate over a moduli space of vacua known to physicists as the Coulomb branch. It's called the Coulomb branch because the low energy effective theory has an unbroken U1 gauge symmetry, which will be very important in what follows. So this Coulomb branch integral is defined in general for class S theories, and will have, and it will be an integral, naturally enough, over the Coulomb branch of a holomorphic and metric independent function in red, curly h, and a non-holomorphic and metric dependent theta function-like object, which I'll describe in great detail. Here, B is the Coulomb branch. In class S theory, it will be the base of a Hitchin system, but for today, it's just going to be the complex plane, and we'll identify that complex plane with a modular curve. So let's do that. Let's talk about the Seiberg-Witten formulation of the low energy effective theory of this theory. So Seiberg and Witten taught us that to describe the low energy physics, we need to give a holomorphic family of Riemann surfaces equipped with a meromorphic differential. For the n equals 2 star theory, here is the holomorphic family. It's a holomorphic family of elliptic curves. The cubic in the elliptic curve is explicitly factorized, and the roots depend affine linearly on u, the coordinate on the Coulomb branch, and the mass squared, and then EI of tau uv are the half periods of another elliptic curve, not to be confused with E sub u. The other elliptic curve is, let's call it the UV elliptic curve, is defined by the ultraviolet coupling constant. As I said, we also have to equip this with a meromorphic 1,0 form, and it satisfies the property that d lambda du is the Néron differential on the elliptic curve. You can easily calculate the discriminant of this family of elliptic curves. It has 3 roots written here, and here it is in pictures. So the picture is that over the u plane, we have a smooth family of elliptic curves which degenerates at 3 points on the discriminant locus. I'll call the complement of those 3 points B star. Okay? Now over B star, we have smooth elliptic curves, so we have a lattice given by the rank 2 lattice, given by the first homology of the elliptic curve. That's a local system over B star. It has monodromy. And by definition, a duality frame is a local choice of basis of that lattice, of A and B cycles. If I have a duality frame, of course, there's no global duality frame because there's monodromy. If I have a local duality frame, then I can do the following. The periods of lambda define a homomorphism called the n equals 2 central charge from H1 to C. And given a duality frame, I have functions called A and AD. And in n equals 2 geometry, there's this really amazing fact that there's a locally holomorphic function called the prepotential, so that if I know A, I can compute a dual by a derivative. So I told you that the derivative of lambda is the Néron differential, so dA du and dAd du are the ordinary periods of the elliptic curve, so the ratio tau is the second derivative of A. So that defines a function tau of u, at least given a duality frame, and it should not be confused with tau uv, although it does equal tau uv in certain limits. Very importantly, as u goes to infinity, tau of u goes to tau uv. Okay, so now we need to know the prepotential. As u goes to infinity, there's a canonical duality frame, the so-called weak coupling frame, and the prepotential looks like this. It has a classical term that looks like that, plus a one-loop term, plus an infinite sum of instanton corrected terms. Here, the Fn of tau uv's are polynomials in E2, E4, and E6. There's an algorithm for computing them given in these papers, but I am not aware of an explicit formula to all orders. The lambda dependence was overlooked before, and we derived it with Xinyu Zhang using the necrossive partition function, and it's actually important in these topological quantities because, as I mentioned before, everything topological only enters through the dimensionless ratio m over lambda. Now, remarkably, you can invert the resulting equations for tau as a function of u to write u as a function of tau. So you can write the periods in the weak coupling duality frame, the periods of the elliptic curve, or rather their square, explicitly in terms of tau and tau uv. And you can write the u parameter. Instead of tau of u, you write u of tau. So the u parameter is written in terms of these half periods of tau, uv, and tau. This way, we identify the u-plane, the base of our Hitchin system, with a modular curve for gamma of 2, which I'll further identify with a fundamental domain for gamma of 2. And it's this pink domain here. So the 3 cusps, u1, u2, and u3, are shown here. There, tau goes to 0, 1, and an I infinity. And then as u goes to infinity, tau goes to tau uv. So So our measure is going to be singular at these 3 cusps and at tau uv. So we have to cut that region out and then take an epsilon disk going down to 0, and that's our Coulomb branch integral. Well, we better first formulate the measure before we talk about the integral. So here's the measure. It's d tau wedge d tau bar, and holomorphic function h times a psi function, which is really just the Maxwell partition function. Let's begin with that. And I'll explain it in 3 successive steps of increasing precision. So to 0th order, psi is just the sum over the fluxes of e to the minus classical action for the Maxwell field. Remember, on the Coulomb branch, there's an unbroken U1 gauge symmetry, so there's a Maxwell field, once I choose a duality frame. Indeed, since I have to choose a photon, it's frame dependent. The Maxwell action is not holomorphic, and it's metric dependent. Now, the metric dependence sounds bad in a topological field theory, but it's very mild in a sense. It only enters through something called the period point. Let me explain what the period point J is. Well, first of all, when B2 plus is bigger than 1, the Coulomb branch integral vanishes from fermion 0 mode, so we don't need to worry about it. When B2 plus is equal to 1, the second cohomology space is a Lorentzian space. And then there's a unique point in the forward light cone that squares to 1 and is self-dual. Now, the self-dual condition is metric dependent. Therefore, J is metric dependent, but all metric dependence comes through J. So in particular, with that J, I can define the self-dual and the anti-self-dual projections of the photon field strength, denoted little f. So little f plus is the self-dual projection of the photon field strength. So in our next level of precision, this is the sum over fluxes of the Maxwell action. It looks like this. What is the sum over fluxes? It's a sum over the first Chern classes of the U1 bundle. And if you're careful, that those classes will be in twice the integral cohomology lattice plus an integral lift of the 't Hooft flux. So here's the official definition of psi. We sum over this lattice with lattice vectors little lambda. We have q to the minus 1/4 lambda squared. What is z? Z is given by CUV. So CUV is the characteristic class of the spin C, the ultraviolet spin C structure. It lives in the second cohomology lattice. It multiplies a complex number v, which is a function of tau and tau uv, and v is the second derivative of the prepotential with respect to a and m. And if we insert observables, we add that term there. So here again are the equations I wrote. I have to tell you what capital E is. Capital E is an error function. Here's my definition of the error function, integral from 0 to x. And the argument of the error function is lambda plus mz over m tau dot j. So x lambda depends on metric because j does, and it's clearly not holomorphic. So all of the non-holomorphian metric dependence is in that error function. Okay, now let me make a physics remark. If you unpack that Maxwell partition function and ask what is the coupling to the background spin C structure, it looks like this, where again V is the second derivative of the prepotential. And that's interesting because it violates folklore. So for Jan and myself, progress was delayed for a long time because we thought, we were assured by folklore that the coupling to the background spin C structure would be holomorphic. And there simply isn't any single valued measure that has a holomorphic coupling. That's actually important if you want to try and derive all this stuff from the 6-dimensional 2-0 theory, because the 6-dimensional 2-0 theory involves self-dual 2 forms. That means you have to use quadratic refinements. The usual quadratic refinements are Z2 valued, but because this term here, which is kind of a shadow of the quadratic refinement in 6 dimensions, is C star valued, I expect that the formulation of the self-dual 2 form in 6 dimensions will involve a C star valued quadratic refinement. That's an example, another example of the kind of thing I mentioned at the beginning, that we learn important general lessons about how to generalize to other theories by studying this theory in detail. Okay, now in order to really understand the measure, you have to know this function v very well. So v is the second derivative of that prepotential. by homogeneity of the prepotential, it can be written in terms of AD and A, but AD and A are very complicated, so that's not terribly useful. Now, Jan discovered an amazing fact, which is that if you take the ratio of Jacobi theta functions of v comma 2 tau, then the resulting thing is independent of u or independent of tau, depending on your point of view. And so you can just take u to infinity. If v goes to 0, tau goes to tau uv. So this is kind of a renormalization group invariant quantity. We give a partial analytic argument for this, and we checked it to high orders in an expansion, but it's still a little bit, it's still unproven. Okay, but it does show that it determines a bimodular object V of tau and tau uv, and using this you can get its behavior at cusps, which is good enough for what we need. Let me say a brief word about the holomorphic part of the measure. So it's a product of holomorphic functions raised to various topological invariants. So we have A1 to the signature of the four-manifold, sigma, A2 to the Euler character, A3 to the CUV squared. If we include observables, we have some more holomorphic functions raised to some other topological invariants. The terms in purple depend on the duality frame. As I stressed, there's a local system has non-trivial monodromy, so it's looking bad for single valuedness of the measure. Here's a formula for that holomorphic function A1, A2, and A3. So A1 to the 8th power is given this by this expression in terms of tau and tau uv. A2 to the minus 4th power is given by that expression, and A3 is given by, again, theta functions evaluated on V. Notice the powers there. You have to take roots. So again, you're going to have non-single valuedness of the various terms in your measure. Nevertheless, with all of these ingredients, we can check that the Coulomb branch measure is indeed monodromy invariant and hence well-defined, and I want to stress that this is highly non-trivial and not at all trivial to check. But it's an important principle. The measure on the Coulomb branch is physical and has to be single-valued. Even though several couplings in the low-energy effective theory are multi-valued, even though there's no global duality frame. In fact, I would like to turn this around and say that this presents an interesting constraint, sort of an anomaly cancellation type constraint on low energy effective couplings. The measure on the Coulomb branch must be physical and single valued. Well, now we have a well-defined measure. What about actually defining the integral of the measure? Well, that's non-trivial because as you go to the cusps, this holomorphic function can diverge. That integer L comes again here. We have Q to the minus L, so if L is positive, we have a potential divergence. And as U goes to infinity and tau goes to tau uv, then we find these kinds of green factors in the measure. Notice especially in the sum over lambda with the coupling to the observable S, we have tau minus tau uv to the minus 1/2 times S dot lambda. So it's looking very bad for convergence of the integral and single valuedness. I already assured you that the measure is single valued, but to make the integral well defined, you take your Q from string theory. Many of you are familiar with this and an interpretation of Borchards lifts. You do the phase integral first, and then you take the limit as you go to the cusp, and then the integrals Jan and I observe are well defined. Okay, so now we have a well-defined integral, so now let's evaluate it. So the basic idea is that after folding up that gamma of 2 domain into a keyhole region for the SL2Z, we're going to end up with a sum of integrals of this form. Some imaginary part of tau to the minus S times some Q series where it involves Q and Q bar, and there can be negative powers, but at least the support of the Q expansion is bounded below. And the whole integrand, of course, is modular invariant. So the strategy for doing this integral is to integrate by parts. So we want to find an H hat such that d tau bar of H hat is the integrand here. And then we integrate around the keyhole region. But what about the contributions from the finite boundaries? Those will go away if H hat is modular of weight 2, 0. Okay, so that's what we want to do. We want to find a solution of this differential equation with H hat modular of weight 2, 0. Okay, now solving the differential equation is a piece of cake. It's a first order differential equation. We have an explicit Q series. We can just do that integral. Okay, and so it's no problem to find a function capital R which vanishes exponentially fast as m tau goes to infinity, solves this equation. The problem is that generally this R will not be modular. But of course, the differential equation is covariant, so its failure to be modular is going to be holomorphic. So that suggests that there should be a holomorphic function, h of tau, which when added to R is going to be nice and covariant and solve the differential equation. If h of tau exists, it's a Mach modular form and it has a Q expansion. If you can find your Mach modular form, you can do the integral, because here you go. You write the integral as a total derivative. The finite boundaries don't contribute. You're left with the integral across the keyhole region at arbitrarily large m tau. That's just the constant term in the Mach modular form. But of course, it's very subtle because that constant term is precisely what's undetermined by the differential equation. It's only determined by the modular properties. So that's the strategy we take. So here again is the Coulomb branch integral. Here's the psi function evaluated on this z. And we want to do it by integration by parts. So write the 2 form omega as d of lambda, where lambda is a 1 form, h is holomorphic. So all we need to do is write psi as d tau bar of g hat. And that also looks like a piece of cake, right? Because psi is written this way. It has d tau bar of e lambda in the sum, and we want to write that as d tau bar of g hat. So why not just write that? That doesn't work because you could have sequences of vectors whose self-dual part goes to plus or minus infinity, and whose lambda squared goes to plus infinity. Yes, goes to plus infinity, so that the red term in Q blows up. And with my definition of the error functions go to plus or minus 1. So this is too naive. This does not work. But it does work if I look at the difference of psi functions for 2 different period points, because with the difference of 2 different period points, I have a difference of error functions. And then if I have these vectors, lambda going to infinity with lambda squared going to infinity, the constant terms and the error functions cancel out, and I now have nice convergence properties. So then, at least for the difference of Coulomb branch integrals at different period points, we can evaluate the integral by sum of residues. And what we discover is that across walls in the forward light cone, as the period point crosses the forward light cone, there's wall crossing that involves modular functions. And also at u goes to infinity, where the modular parameter tau goes to the ultraviolet modular parameter, tau uv, we get actually continuous metric dependence. And closely related to that, from that boundary, we get non-holomorphic dependence in tau uv. And in our paper, we write a very explicit holomorphic anomaly equation with a very explicit kernel k. And so it's some infinite series in QUV and QUV bar. Now, that's the difference of the Coulomb branch integrals. There's a special point where we can actually do the integral without taking the difference. The special point is the point where the psi function factorizes. It factorizes as the theta function of the negative definite part of the cohomology lattice times a function f, which looks just like it was before, but now we're just summing over integers. So now we're in the world of all sorts of modular objects that people are familiar with. So our goal again is to write this as a d of a 1 form and find a g hat, which is well-defined, non-singular away from the cusps and tau uv, and has a good qi expansion. These conditions determine g hat uniquely as a modular completion of an Appel-Lerch sum. So I've written the Appel-Lerch sum valid for one of the 2 Atough fluxes. Again, z is given by cuv times v plus insertions of observables. I have a very good audience of analytic number theorists, so let me mention a very technical point here. So it's important that the g hat be non-singular away from the cusps and tau uv. Now you see in the Appel-Lerch sum, from the denominators in the sum, there's a huge number of poles. Okay, so the poles are in this lattice, and we're substituting z equals cuv times v, and so in general you find a huge number of unwanted poles. So what you have to do is you have to add a meromorphic form to f to cancel those unwanted poles. Now, For the case of a canonical spin-C structure, we found the proper meromorphic function, and we evaluated the Coulomb branch integral, and lo and behold, it's the Mach modular form associated with the Hurwitz class numbers times the theta function for the negative definite part of the cohomology lattice. And so that is a kind of expression that's familiar from Waffle-Witten theory on CP2. For other spin-C structures, you get other Mach modular forms. For CUV equals 1 on CP2, we didn't have to add anything, it turns out. But for higher CUV, well, we know the meromorphic correction exists, but we were not able to find an explicit formula for it. So there's a challenge for people who like really technical challenges. You can also include observables. So this illustrates nicely the fact that we're interpolating between the Donaldson invariants and the Waffle-Witten invariants. So here it is for CP2, where I'm inserting n point observables. So if n is 0, that's just the partition function, and lo and behold, we get the Waffle-Witten partition function. If we look at the terms that survive the mass goes to infinity limit, these are the red terms here, and those are indeed the Donaldson invariants of point operators on CP2. And the rest is a generalization. Okay, I got a few minutes to say something about explicit results when B2 plus is bigger than 1. So in physics, we realized, Zyberg and Witten realized that at the cusps, at the points in the discriminant locus, the description of the low energy effective theory changes. And so we have to have a whole new contribution to the path integral from the low energy effective theory in those 3 points of the discriminant locus. And then we add all the contributions for the full partition function. So it looks like this. Now, when B2 plus is greater than 1, as I mentioned, the Coulomb branch integral actually vanishes, and we get true topological invariance. So we have, it's very interesting to determine these 3 effective actions associated with these 3 points in the discriminant locus. Now, a nice argument from my paper with Witten is that the behavior of the Coulomb branch integral at these cusps actually uniquely fixes that low energy effective theory at the cusps. That's why the Coulomb branch integral is so important, because using it, you can actually get the low energy effective theory at the cusps, which determines your partition function. And the result of a long story is that the contribution from the cusps looks like this. It's a sum over spin-C structures, which should not be confused with the ultraviolet spin-C structure used to define the theory. This is a sum over what I'll call the infrared spin-C structures. So it's a sum over infrared spin-C structures of the Zyberg-Witten invariant, that's an integer associated to the spin-C structure, of various holomorphic functions of tau uv and t raised to the power, which is a topological invariant. What topological invariants do we get? Well, there's Euler character and signature, which are best organized as these linear combinations. There's CUV squared, which is best organized as this integer L. We also have a sum over the infrared spin-C structures. As I said, it's nice to define a vector x, which is CUV minus CIR over 2, and then we have another topological invariant x squared, and now if we include observables, we have some more topological invariants. Okay, so now the name of the game is you use the Coulomb branch integral to determine these 12 holomorphic functions. Here's the result.
Greg, you have about 10 minutes.
Okay, thanks. So here's the result. So, you, in the 3 boxes, you have the contributions from the 3 cusps. What you see here is various modular functions raised to these various topological invariants I was just talking about. In this, look at the top box. You have a sum over x. That's a sum over the spin-C structures of the Zyberg-Witten invariant, an integer, with this modular form, theta 3 over theta 2 to the x squared power. And similarly at the other 2 cusps. If you want to, no, sorry, this is just the partition function with no observables at all included. If you want to include the observables, then in that sum over spin-C structure, you have things like e to the s dot CIR times a modular function. That's what you see in the first column here. The 3 terms, 3 rows of the columns are the 3 cusps. And similarly for s squared and s dot CUV. Now you can use all this and work out the modular transformation law, and it looks like this. There's a weight, which is minus chi over 2 minus 4 times that integer L. In Vafa-Witten theory, it's minus chi over 2. You have a representation, B mu nu, of the modular group, and the surface observable and the point observable transform with weight minus 2, and the point transforms with a shift. Okay, and for the experts, I should mention that there's actually not one non-abelian rank 1 theory, there are actually 3. The SU2 theory and the SO3 plus and the SO3 minus theory, and the partition functions of these 3 theories are permuted according to this diagram where the red arrow is T-duality and the blue arrow is, the red arrow is the S transformation of the S-duality group, and the blue arrow is the T transformation of the S-duality group. Let me conclude. So I got a few slides here. I think I can do it in time. So first of all, let me comment again on the relation to the previous results I mentioned at the very beginning of the talk. So for the canonical spin-C structure and the mass goes to 0, we recover and generalize the formulae of Vafa-Witten and Dijkgraaf-Park and Schroers for the Vafa-Witten invariants. For a spin manifold with 0 spin-C structure, we recover formulae from a paper of Labastida and Lozano. For the mass goes to 0, for the mass goes to infinity, and QUV goes to 0 in a coupled way, so that we go back to the pure SU2 theory. After a suitable renormalization, there's a whole story there. After a suitable renormalization, we indeed recover the Witten conjecture for the Donaldson invariance in terms of the Seiberg-Witten invariance. So this is a big generalization of that formula. Now the general evaluation of the U-plane in terms of Mach modular objects recovers and generalizes explicit evaluations for special form manifolds that go back to the late 90s. And so basically what I'm saying is that this is a generalization and unification of the 1990s results. Now recently there have been some papers discussing the holomorphic anomaly from other points of view. So for the longest time there was no physical derivation of the holomorphic anomaly proposed by Vafa and Witten in 1994, but just in the last few years now there have been 2 other papers deriving it physically, and my paper with Jan gives an independent derivation. So now we really understand it from the physics. Also, in the last few years, a group of mathematicians, Goethe, Kuhl, Nakajima, and Williams, have been writing a beautiful series of papers on enumerative algebraic geometry of moduli spaces of sheaves on projective surfaces. And amazingly, they have formulas which are identical to these formulas here. So you have to translate the notation a little bit, but these formulas, as you see, are extremely intricate, and they have the same formulas. Although Jan and I are addressing a slightly different question. So let's compare with GKNW. So we're talking about a general form manifold admitting an almost complex structure. They're talking about a projective algebraic surface. We're talking about an arbitrary spin-C structure. They're using a special spin-C structure canonically determined by the complex structure, but they do something we didn't do. They refine their formulae to include what's called the chi-y genus, and we don't know what that is physically, so Jan and I have been working on that, trying to understand how to derive that from the physical point of view. Here's a conjecture from Goethe, Kuhl, Williams. This is the kind of formulae that they get for the chi-y genus. So you see interesting infinite products here, modular infinite products. Think of x squared as q. And as y goes to 1, many of those interesting products go to 1. So we don't see that yet. We'd love to derive that from the physics. Another important lesson that we learn for large T is that quantities defined in the UV, like the integral over the instanton branch and the abelian branch, actually correspond directly to quantities in the IR. That is very surprising, but in view of the time, I think I'm going to skip over that. So, future directions. If X is complex, it would be really nice to compute these refined versions. So I'm discussing that with Jan, and that's related to another discussion that was initiated recently by Xinyu Zhang, where he proposed that there should be an interesting generalization of all this story to the 5-dimensional super Yang-Mills theory. And so we've been discussing that a little bit, and I hope that's an interesting topic for the future. As I've alluded to several times during the talk, it would be really interesting to derive all this from the six-dimensional 2-0 theory and to generalize all these ideas to topological invariants of general theories of class S. So with that, sorry for the interruption. It was a very important interruption for me. I apologize for that at the very beginning of the talk, but thank you for your attention.
Thanks a lot, Greg, for that beautiful talk. Yes, we do have time for questions. So please, if someone wants to ask a question, you can go ahead and unmute yourself.
Okay, I went too fast.
It was crystal clear. That's why. Okay, but then I remind you that Greg will also be around for the discussion session, so you can chase him down in one of the breakout rooms. But let's thank Greg again. And then we will break now for about 17 minutes, and we will reconvene for Samir's talk at, this is so difficult to convert, 4:45 UK time. Thanks.
So now it's our great pleasure to have Samir Murthy from King's College London, who will give us a countdown from 5 to 4 to 3, as you can see on the title. Please go ahead.
Okay, thank you very much for the invitation and for the nice organization of this workshop. Pleasure to give this talk. The main physics question underlying my talk is to account for the statistical origin of black hole entropy. And string theory has been very good at doing this. It's one of the successes of string theory. And as many of you here know, that effort has also led to many connections to modular, modular, automorphic forms of various types. We heard one example in the talk of Boris yesterday. Now, today I want to describe such a connection, but in a slightly different and perhaps broader context, namely that of ADS-CFT, which is a conjecture which relates gravitational theory in 5-dimensional spaces to gauge theories in 4 dimensions. And in this context, I asked the same question, namely, what are the microscopic states of a supersymmetric black hole in the variables of the 4-dimensional gauge theory? Now, this question itself has been around for about 15 years or so. And there's been some new progress in the last 2 or 3 years. This is what I want to discuss today. Everything I talk about, well, most of what I talk about will be joint work with many people, Davide Cassani, Dario Martelli, and mainly Alejandro Cabo Bisset. And then towards the end, also Arash Arabi Ardehali. These two are postdocs with us at King's. And what we find is that the microscopic states of supersymmetric black holes in ADS can be described in terms of an integral over unitary matrices, which arise from 4-dimensional super-Yang theory. And the calculations that I'll describe really begin as some asymptotic developments of certain infinite products. And in doing these calculations, we find relations with, firstly, 3-dimensional Chern-Simons theory. I hope to get to this by the end of the talk, but if I don't have time, then that has to be postponed. But more interestingly, for this audience, relations with functions arising in number theory, most notably a Kronecker-Eisenstein series of the type that we've already seen at least 2 times in this conference, maybe 3 times. And the one I'll talk about has relations with the elliptic dilogarithm of Bloch-Henry. So I'll come to all this. So let me then begin by as the organizers asked, by just laying out an explicit mathematical problem. So here it is. I've tried to be as precise as possible. Calculate the following n-dimensional integral. Okay, so this integral is a function of tau, which is in the upper half plane, and the variables of integration live in R mod z, and the integrand is a function of two variables. It's actually a specialization of a function of three variables called the elliptic gamma function, which has been studied by Felder and Marchenko and Spiridonov and Vartanov. But in this specialization, it's actually much simpler. It looks like this. It's essentially a ratio of McMahon functions with an insertion of another parameter, zeta. Okay, so that's the problem. So the problem is to evaluate this integral. I'll just leave this for a few seconds in case. So the next 20 minutes or so, what I want to do is to explain the physics of this, where this comes from, why this is interesting, and what we expect from physics. But in case you want to zone off, then and you just want to think about this and calculate this, I'll just leave this for a few seconds. And after 20 minutes, if you have any comments, please do let me know. Okay, so then I start with a bit of physics. So the starting point is, so there are two ideas from physics that I'll use to set up the main problem. The first one goes back to Bekenstein and Hawking in the 70s, who said that given any black hole, this is a solution of Einstein's equations, which is surrounded by a one-way surface called the event horizon. So given any such solution to Einstein's equations, you can associate to it a thermodynamic entropy, which is equal to the area of that horizon divided by 4, divided by the Newton's constant. Now, combining this with the Boltzmann equation, which says that any thermodynamic entropy must be interpreted as the logarithm of the number of microscopic states of a system, one can associate some integer to every black hole. Okay, so that's the first idea. Of course, this statement is not quite precise. Boltzmann meant this in an asymptotic sense, and I'll try to make this more precise in the context that we have. Okay, but roughly, this is the idea. Given a black hole solution, you can associate some integer number of states to it. Now, to actually understand what these states are, one needs a quantum theory of gravity. And that leads to the second idea, namely the ADS-CFT correspondence, which conjecturally tells you what is the quantum theory of gravity for a type of gravitational theory. So this is a 5-dimensional theory, which is asymptotically ADS. ADS stands for anti-d zeta. What that means is that there's in the 5 dimensions, there's a radial direction going from 0 to infinity. And near infinity, so asymptotically, the space is a hyperbolic space. Okay, the space of constant negative curvature. And the conjecture relates the quantum theory of gravity on such a space to a gauge theory living on the conformal boundary, the asymptotic boundary of that space. Here I've taken that to be S3 times time. Okay, so this is where the gauge theory lives. And so the picture is supposed to be as follows. So the gauge theory lives on the boundary of this, lives on the sphere. And here I've cut open the sphere. In the gravitational theory, it's like a solid ball whose boundary is the sphere. Okay, so black holes will live somewhere inside the sphere. Okay, now so this is the prototypical example here. So the gauge theory in question is maximally supersymmetric Yang-Mills theory, n equal to 4 Yang-Mills theory, which is exactly the theory, which is one of the theories we heard just now in Greg's talk. So this has two parameters, the rank of the gauge group, and another parameter called the 12 coupling, which is a real positive number. Now, correspondingly, the gravitational theory has two parameters, Newton's constant and the inverse radius of curvature of the hyperbolic space in Planck units. And the conjecture starts by giving you a dictionary between the parameters. And lambda here is like an interpolating parameter. So on the gauge theory side, you have perturbation theory in lambda. And on the gravitational side, you have a perturbation theory in 1 over lambda. And this is what makes the conjecture non-trivial and also difficult to check because you need to calculate. If you want to compare, then you need some quantities either exact in lambda, or another strategy is to look at observables which are independent of lambda. And that's the kind of thing I'll be doing. These are supersymmetric observables.
Samir, these are string units, because I don't understand the units otherwise.
In 5-dimensional Planck units.
Ah.
All right. So this is the equation I ask you to remember, that 1 over n squared is g Newton. Very good. Now, we put these two ideas together and formulate the main physics question. So this is the same setup as I just described. Now this gravitational theory admits black hole solutions, and in particular, solutions that preserve 2 of the 32 supercharges of the theory. These are called 1/16 BPS black holes. And these are labeled by one integer. And the entropy of these black holes are a function of that integer divided by 4 times Newton's constant. And because g Newton is 1 over n squared, if you fix the other quantities appropriately, this scales as n squared becomes large. Now we want to ask, what is the statistical entropy of these black holes? The natural place to look are the 1/16 BPS states in the Yang-Mills theory. And there is a quantity called the superconformal index, which gets contributions from these states. Okay, so it's defined as a trace over the Hilbert space in Yang-Mills theory of this fixed charge. I'll explain this a little more. And the main question is, and this quantity is protected, it's independent of lambda. So the question is the logarithm of this? So the moral question is, does this index capture the black hole entropy? In other words, is the logarithm of dn equal to the black hole entropy? Okay? And even at a more basic level, does it scale as n squared in the way that the entropy is supposed to scale? Okay. So this question was first formulated and investigated in this very nice paper. And at that time, the answer seemed to be negative. Okay. And then there are many possible sort of subtleties in formulating this question, and I'll discuss a few of them. But in the last few years, there's been new progress, and we've understood that, in fact, not only does this log of the index scale as n squared, but in fact, you get on the nose the black hole entropy including this function. So that's what I want to discuss. And I'll try to get progressively more precise as we go along. So first, what I'll tell you about is a little bit about what this index is, what these black holes are, and what is the meaning of this expectation. Okay. But please do ask questions at any point of time. So for instance, now. All right. So let me then describe what this index is. So any quantum theory comes with a Hilbert space, and that Hilbert space is decomposed in representations of the symmetry algebra of the quantum theory. So any pool of 4 super Yang-Mills, again, we heard the symmetry algebra of this theory in Greg's talk. Here I'll be using sort of only a few of the generators of the algebra. So time translations, which is R, and a certain U1 symmetry called the R symmetry. This is a subset of the larger R symmetry groups that Greg discussed. And their eigenvalues are called E and R. And the fact that this theory is living on S3 means that there's an SO4 symmetry, and the reps now are labeled by 2 half integers, J1 and J2. Okay. Now, in addition, there is supersymmetry. So again, I won't say very much. Greg explained all this very beautifully. I'll just be very basic. It means that so firstly, that the whole theory has some Z2 grading into bosons and fermions. The grading is called -1 to the F. +1 is bosons, -1 is fermions. And there's a fermionic generator called curly Q, which is complex. So QQ bar anti-commute to this combination of these charges, E, J1, J2, and R. And we focus on states, BPS states, which means that they're annihilated by Q and Q bar, which means that E is completely determined in terms of J and R. So we can just focus on these 2 charges. And now the rules of the superconformal index of constructing protected quantities. So I won't discuss this. It'll take me another 5 minutes, but I don't want to spend those 5 minutes. The rule is that you should look at charges which commute with the supercharge. Okay. So neither J nor R commutes with Q, but one combination 2J plus R actually commutes with the supercharge. So the index is built as follows. It's a trace over the Hilbert space. This is the full Hilbert space of the theory, times minus 1 to the F, times e to the 2 pi tau. Tau is our tau parameter, times 2J plus R. Okay, so this is the sort of simplest superconformal index to which these 1/16 BPS states contribute. The whole story can be made more complicated and everything works, but I don't want to discuss any extensions. So this really is sort of a generating function of indices. This in the index, you should think of a Fourier expansion. There's a 3 here for reasons of convention. Physicists will immediately recognize this. This is the fact that the R charge of n equal 4 super Engel's theory is quantized in units of 1/3. Okay, so these dn are the superconformal indices for fixed charge n. N is 2J plus R. This in is also sometimes called the index. So this is the index is a generating function. Sometimes I'll call this the index function, or as in physics, I'll call this the microcanonical index and the canonical index. Okay, they're just related as such. Okay, so that's the superconformal index. Now let me tell you a little bit about black holes. So the black holes in question are solutions of what is called minimal ADS5 supergravity, which is a theory of the metric and one gauge field. And the charge of this gauge field is precisely this U1R charge that I talked about. And the simplest supersymmetric black hole also has charges J and R, can be labeled by these charges. And in gravity, one often scales out the Newton's constant, n square, and writes gravitational charges small g and small r. Now, these are 2 charges, but in fact, if you look at this black hole solution in supergravity, you find that those two charges are not independent. There's a relation, which is a little bit complicated, but it's completely explicit. You can write it down. Here I've shown you the nature of that relation. So for large charges, it's something simple. Okay. So in effect, there's only one independent charge, and you can choose that to be 2J plus R as before. And therefore, if you measure the entropy is a function of these charges. There's this 1 over g Newton as should be, and times a function of the gravitational charges. And you can write this as n squared times 1 function of the gravitational charge small n over n squared. Okay. So the black holes, so the summary so far is that the black holes of the type I'm considering are labeled by one integer n, and the entropy is given by one function, and so is the superconformal index, dn of n. And the question of Bacon-Stein-Hawking translates as follows: is log of dn asymptotically equal to the black hole entropy? All right. Now let me. So this entropy is some specific function. Again, it's a little bit. The formula is a bit complicated, but it's completely explicit. Here I show you. That's the right-hand x-axis is the charge. The y-axis is the formula for the entropy. And here you see the sort of 2/3 growth of the entropy. And in this direction, you also see the n square growth of the entropy. All right. Now, what does this asymptotic condition mean? So there are 2 limits which people discuss. So the first one is what comes from physics. It's called the large n limit, which means that the charge and the rank of the gauge group both go to infinity, with the gravitational charge being fixed, n over n square being fixed. Mathematically, this is more subtle to define because you're sort of changing theories and changing the charge at the same time. One has to ask whether there is such a limit and so on. There's another limit which people discuss, and this is sort of much easier to define mathematically. It's called the Cardy-like limit. Namely, you just fix n. So n, remember, is the rank of the gauge group. So you work in SU2, SU3, whatever you want, and then just take the charge to infinity, and you ask whether asymptotically this equation holds. Okay, so that's neither of these 2 limits are subsets of each other. They're completely different limits. There's a regime of overlap when both the charge and the ratio is very large. Okay, this is the regime when the black hole becomes very large and sort of fills up ADS space, so to speak. Okay, any questions so far? Very good. So then the next thing I want to discuss is the following. So in number theory and in many parts of, in combinatorics, in many parts of mathematics, when you have a sequence of such integers, so the rule of thumb is to sort of make them into a generating function and study the properties of that function. Okay. But in fact, in physics also, this principle is very well understood, and it's been understood for more than, this principle operates for more than 100 years, even in thermodynamics, and in physics we call it the change of ensemble. Okay. So these will be called microcanonical ensemble, but in fact, even 100 years ago, people were not studying of gases with fixed energy. They were fixing the temperature and then asking what happens to the microscopic phase of the gas. So that's called the canonical ensemble. And in gravitational thermodynamics, black hole thermodynamics, Gibbons and Hawking explained what that, how to go between these two ensembles. Okay, so if you have a sequence of integers, you literally just take the sum. Here it's slightly more complicated. If you're given a black hole solution, you're supposed to look at some the on-shell action of the areas. Okay, so I won't discuss this, but I want to say that for supersymmetric black holes, this procedure turns out to be singular. There's a subtlety. So this is a physics slide, but I want to say it. It's singular. Singular because the supersymmetric black holes have an infinite throat deep inside the ADS, and one has to regularize. And that's what we did in this paper. And what we found is that, so you do the regularization as follows. You keep the condition of supersymmetry manifest, you go away from extremality, and there you have well-defined sort of finite horizon geometries. So this is what you expect.
Sorry, Samir, could you say more about what that throat is? The throat is at the horizon, is that right?
Yeah, so let me say it properly. So you take the ADS black hole solution, right? So if you have a thermal black hole, then you look at the Euclidean solution, then you'll get some cigar geometry. Okay, so there's some infinity coming from the asymptotics of ADS that you have to subtract, let's say, with background subtraction or something like that. For supersymmetric black holes, there's another infinity coming from the fact that as you go near the throat of the black hole, because it's supersymmetric, you don't get a cigar, you just get an infinite cylinder, okay, in the infrared. Is that clear?
How did you go from the cylinder to the cigar?
So here, you mean in this picture. So let me explain this picture. So the black hole is living here, that's the cylinder. Now it turns out that there is actually a 4-parameter family of solutions of which this black hole is sort of a codimension 2 object. So what we do is if you look at solutions and you impose supersymmetry, but not extremality, then you still get good solutions to the theory. These are not good Lorentzian solutions. They have closed time-like curves. But in the Euclidean theory, they're perfectly well defined. They are cigar-like solutions. They're not extremal. That's why you have a cigar-like object.
I see. Okay.
You go here, and then the Gibbons-Hawking procedure is fine. You can just calculate the on-shell action as usual. It's finite after the usual regularization. And then you take a limit towards the black hole. So that's what was spelled out in this paper. And when you do that, what you find is that, in fact, the action is independent of beta. Okay. And therefore, you can just read off what is the canonical free energy of the black hole. Okay. So I've translated to units of n and tau. And it's pi I over 27n square times 2 tau plus 1 cube divided by tau square. Okay, this is a function which will appear again and again. So I'll try to remember. It's n square times the cubic divided by quadratic. There's more to say here. This picture also, so for the physicists, this picture also says why the supersymmetric black hole actually contributes to the index. So there's these kind of questions. I don't want to get into that now, but maybe you can ask me after the talk if you have questions. All right, so that's the status. So this was about 2 years ago, and after that there were many developments, and which is what I want to discuss. So in going to the canonical ensemble, you've actually done two things. Firstly, you've simplified the problem. So instead of looking at the sequence of integers and asking whether it's asymptotically equal to the entropy, you look at the generating function of the index, canonical index, and the translation is simply whether the log of this function of tau equals this function that I just showed you, n squared over 27 pi I, 2 tau plus 1 cube divided by tau square. And the two limits that I showed you have a translation. So the Cardi-like limit is you fix the rank n and just take tau to 0. The large N limit is more subtle. I'll just say something here and come back to this after some time. So you essentially fix tau and take n to infinity. So again, it's not mathematically obvious that this is a well-defined limit, but in physics, we expect that there is such a limit, although we don't have a formula for it, even conjecturally. Okay, so now this is what I want to deal with. So all this was sort of a physics background to set up this problem. What I want to do now is to focus. So the main player of the talk will be this function. So it's a function I showed you on the first slide, and I want to analyze that function. And this is the expectation from physics. Notice already that whatever this function is, it's not a holomorphic modular form under SL2Z, because such things near tau goes to 0 have a 1 over tau and not a 1 over tau square behavior. All right. So let me now describe what this superconformal index is. Again, unless there are other questions, let me just pause for a few seconds. All right. So this index begins its life as an integral over unitary matrices of size n. Okay, n by n unitary matrices U of an exponential of an infinite series. Each term in the series looks like trace u to the n, trace u dagger to the n, and the series is controlled by one function, which is this explicit function I've called here. It's called the single particle index. Okay. Now again, this is well known. Why this is the correct counting function, I don't want to discuss. It's fairly standard. Just to give you some sense of it, this F, so this gauge theory is made up of gauge invariant words. So there's a Lagrangian and there are letters which are the fields of the theory, and you're supposed to put them together and count how many operators there are. This F roughly counts how many operators contribute to this index, how many letters contribute to this index, called the single letter trace. This exponential essentially makes beads and necklaces of these words, of the letters, and makes words. So it's a standard combinatorial problem. And then the integral over the group projects you onto the gauge invariant. So this is like fairly standard invariant, basic invariant theory. Okay, or you can understand this using supersymmetric localization. Anyway, I'm going to take this as a given. And now, what do we do? So what we're taught to do when faced with such an integral over matrices is you first diagonalize the matrix. These are the eigenvalues. The small ui I'm going to call eigenphases or eigenangles. And this Haar measure on the group, you write in terms of the flat measure of these eigenphases. And then you'll get some van der Monde determinant, in which you can exponentiate, and you'll get some big action of this type. Now, the van der Monde determinant is only a function of the differences of the eigenphases. That's a familiar fact. This matrix model has a particular feature that even the original action itself is a double trace, and therefore the whole action is a sum over pairs of interactions. If I think of the eigenvalues as some particles, there's a potential which depends only on the distance between the two particles, ui minus uj, and it's summed over all pairs of particles. This is some constant which is not going to affect most of the considerations. Okay.
Samir, can I ask you a question? So it isn't obvious to me that this thing has a Fourier expansion in tau.
Not yet. You'll see it in one slide. So just hold your horses for 1 minute. So here it is. So if you actually calculate this f, okay, this infinite series turns into an infinite product because of the exponential, and then you can just calculate it, and you'll see that that becomes exactly what I showed you on the first slide. And now you can see that the gamma function is periodic in Z with period 1, because it only depends on zeta. Sorry, I should have said this again. Q is e to the 2 pi r tau, zeta is e to the 2 pi r z. So this is periodic in Z with period 1. And because there's a 2/3 here, the whole integral is periodic in tau with period 3. Yeah?
Thank you.
All right. Okay, so that's the end of the physics introduction. How am I doing with time? So. Okay. So in the next sort of half and a little bit of the talk, what I want to discuss is I want to discuss this integral. So now it's a completely explicit integral, and show that it indeed obeys the expectations that we have from physics, and then analyze it a little more. Okay. So the first thing I want to say is that for a fixed n, this is a completely explicit function. So one can just study it on the computer and ask whether the expectation is at least roughly satisfied. And this is what it looks like. Okay. So what I've plotted here is for various ranks. So this is UN gauge group, start U2, U3 up to U10. And the solid lines are the black hole entropy formula for that rank. Okay, this is my expectation. And the dots are the logarithm of the absolute value of the index for a given charge. The horizontal axis is a charge. Okay, and you see many things here. So the first thing to see is that by and large, there's a very good agreement with what is expected. Okay, so the baseline is established. Now you can sort of try to do more sophisticated experiments. So firstly here, notice that I plotted the absolute value, which is not what you should really do. But if I actually plotted D, I would have some enormous oscillations. And once I've established this baseline, I can divide by it. I won't show you the numerical experiments, but already with this plot, you can see lots of patterns. So one pattern you can see, at least for which becomes clearer at higher n, is there's this oscillation. Okay, so here it's most clear. There's oscillation, which is, at least to the naked eye, is periodic. And then there is this sort of dive down towards negative infinity. And that's really a sign that you should plot it in a better way. That's because I'm plotting a log, and that looks like a log of 0. That's exactly what is happening. Okay. So what I want to do now is to sort of explain. So I won't explain everything about these graphs, but what I want to explain is at least the rough behavior and a little bit about these oscillations. There's another interesting feature here at low charges. There is not an oscillation. It looks different. That also I can explain, but I won't have time to do that. You can ask me after the talk. Okay, so now I'm going to switch to my iPad. Which is to stop here. So in the meantime, you can ask me questions. Share, AirPlay, share. Mirroring. Okay, do you see this?
Yeah.
Perfect. Okay, so let me start again. I've just written down the definition. So that's the superconformal index as an integral over these n parameters ui. Okay, so this is this elliptic gamma function. And so this was already asked. So this is periodic with period 1. And therefore, the index is periodic with period 3. Okay, so that's the Fourier expansion, like I showed you. So first, actually, let me tell you a little bit about these microcanonical indices. So if I want to describe, so let me just calculate this. So that this, I just invert this formula, so it's an inverse Fourier transform, like so. Okay, and I want to start to calculate this. Right. Now, if I want to calculate it, the natural thing, so first I want to ask what happens when the charge becomes very large, n goes to infinity. So the instinct is to do some kind of a saddle point approximation. And that so when n goes to infinity, we'll say that tau goes to 0 in the saddle point. But in fact, if you think about it a little bit, what really goes to 0 is the imaginary part of tau, not just tau, because the way things are here. And the real part of tau can be any rational number. Oops. Okay. It has to be rational because sort of you want a good asymptotic limit. So let me focus on that a little bit and explain what is the. Let me just explain a little bit what this real part of tau is doing. It's very elementary what I'm going to say, but it's a bit important, so I'll say it. So suppose you have a Q series of this type. Okay, so f of Q is some df of n q to the n. And I want to ask, what is df of n? So df of n, so now I've gone to the variable q, which is e to the 2 pi tau. So df of n is written as a contour integral of the following sort. So f of q, so well-defined, let's say it's a holomorphic function in the unit disk, and near the on the unit circle, there might be some singularities. That's typically what happens. So you write this contour integral. So this contour is some arbitrary contour inside the unit disk. And then you ask, you take this contour and you take it towards the unit disk and make it go towards a singularity. So many times, for instance, the dominant singularity is at tau equal to 0 at q equal to 1. And then the dominant part of the integral comes from this part of the contour. Okay, this is the standard circle method. And I think in this conference, everybody knows this very, very well. So if you take, for instance, 1 over eta of tau, you get the near tau goes to 0. The behavior is singular indeed. It goes like so. And then the saddle point value of this, you have to take this. So is the following integral is some Bessel function, which then you can further write down some asymptotic expansion of the following tau. Okay, so this is completely standard. What I want to say is that the saddle lives somewhere here. Okay, so it somewhere very close to 1. So tau equal to 0, and looks like this as n goes to infinity. Now, suppose you have a different example. Suppose you say, I define a function g, which is the same as f, except that tau is shifted by tau plus half. Okay, so I change the real part of tau, and then write a Fourier expansion as before. Then all I've done is to take the same function and sort of rotate it in the Q plane by half. So now the dominant singularity is over there, and the saddle point now is half plus what used to be the saddle point. Okay, so all this is completely elementary. Now, if I compare f and g, let's see what is happening. So firstly, the values of the Fourier coefficients only differ in phase, okay, because of the shift of half. The imaginary part of the saddle point values are the same. The real parts are shifted by half. And so the real part of the saddle point absorbs this phase oscillation. Okay. So the new function g has a dominant growth at some other point over here. And if you now, for g, if you look over there, the old saddle point, you'll find some subdominant growth. Okay. And as an extreme example of this, you can do the following exercise. So take theta 3 and theta 4, the Jacobi theta functions and their inverses. And you'll see that as tau goes to 0, log of f has a dominant singularity, but log of g, so f and g here are related exactly like as I discussed up here. Log of f has a dominant singularity at tau goes to 0. Log of g not only has a subdominant, in fact, it doesn't grow at all. There's no growth at all at tau goes to 0. Okay, so that's an instructive example. So now let's look at this black hole function that we want, this in of tau. And as it turns out, it's of this type. So near tau equal to 0, there is actually no growth at all. And the dominant growth comes at the other two cube roots of unity. Okay. And so that's the picture. And now if I want to study, so this is really where the black hole is defined. And if I want to study it, then I have to sort of go here and then zoom in. So I'm back to the variables where the period is 3. So I go to tau goes to tau plus 1 to reach the cube root, and then I change variables and then call it tau goes to 0. Okay. So now what I want to do is to study these gamma functions, elliptic gamma functions near tau goes to 0. Can do that, and using the Euler-Maclaurin formula, you can write down what the asymptotics are. And it turns out that it starts with 1 over tau square, then there's a 1 over tau and O of 1. And the coefficients are what are called periodic Bernoulli polynomials. So I used, by the way, an exposition of this due to Don Zagier, which I found very nice and instructive in one of his papers. Bn is the periodic Bernoulli polynomial. This is just, one way of defining it is you take the Bernoulli polynomial and take the real part of z in between 0 and 1, and then translate by periodicity. In other words, you just write down the Fourier expansion and define it using that. Okay, so now that I have that, I can just plot what this potential is. I can just write down in the same asymptotic limit what this potential is, and I get some piecewise polynomial function of this type. And now it's very easy to see where the saddle points are between between these two limits. The saddle points essentially are here. So all these things, all these variables want to condense over there, and then you can read off what the potential is. Okay, so it was very fast, but these are elementary calculations, and that's what we did in this paper, again with Alejandro Cabo Bisset, Davide Cassani, and Dario Martelli. And then there are also other papers one by Kim and Song, which essentially did the same calculation. What one finds is the following. So you get that the log, so I should have said something. So you use the saddle point calculation, and then essentially you can do the integral after using the saddle point value. Oops, now this froze. Sorry, what, Axel, what are you seeing on the screen?
It's still the graph of the
graph.
potential, yeah.
Then is it moving now?
No.
I was afraid of this, but in fact, I've more or less finished. There it is.
No, it's moving. Yeah.
Good. All right. So what you find is exactly pi n square over 27 times 1 over tau square plus.
Sorry, now it disappeared.
Whoa. I'll try again. Otherwise, I'll join by Zoom as one of you taught me. So let me maybe stop share. Sorry about that. I'll try once more and then. All right. I hope I'm back.
Yep, it's working again.
Okay, so if this goes away, then I'll join by Zoom. And here you can see that it's very easy to see that this is equal to 1 plus 2 tau cube divided by tau square plus O of 1. So that's equal to F grav of tau. Okay, so indeed, the leading singularities are exactly that as expected from gravity. Okay, in fact, this technique you can this Euler-Maclaurin formula you can also calculate the complete asymptotic expansion. I'll come back to this, but for the moment, I wanted to show that you get this agreement. And now, if you want to calculate these degeneracies, you plug in this asymptotic value, and then you extremize. And because this is a cubic function, find that the saddle point value is some cube root. And because tau has to be in the upper half plane, one important point is that the correct value of tau is something like that. So oftentimes in these problems, in the simpler problems, you find tau coming in directly from the on the imaginary axis, and here you don't. And that reflects itself in the fact that when you put it back, the contribution of the saddle point to these degeneracies in the exponent has a real part, that's the black hole entropy. But there's also an imaginary part, which is not 0. So what does that mean? Well, you have to add the other cusps. And as I said, there is this sort of complex conjugate cusp, which is not seen in this analysis if you only zoom in at this point. But if you do that as well and add it, then indeed what you get is that the degeneracy looks like the black hole entropy times the cosine of something. And these are exactly the oscillations that you showed. So I showed the log of that, and that's exactly what is happening. Okay.
But the other cusp doesn't have a black hole, a geometrical interpretation?
That's a very good question. Let me pause on this question. I want to say a little more than this. Please ask this after 10 minutes. So now recall that, so you had two cusps, but in fact, there are, in the problem, you can expect many cusps. So both from the physics side of it, because you can have other asymptotically area solutions, also from mathematics, because you can ask what happens at the other rational points. Okay. So that's what I want to answer now. I'll stop sharing again and get back to my computer.
So you have about 15 minutes left, by the way.
Thanks. Except that I lost my, sorry. Ah, here it is. Share. There it is. Okay, can you see it?
Mm-hmm. Yeah.
All right, great. So, so one thing one can do is to do a similar asymptotic expansion at all cusps, but I want to show you something else, another method to talk about the other cusps. So this is the large N limit. So I get back to this matrix model. So and now this what I'm going to say next is collaboration with Alejandro Cabo Bisset. And what we said is, well, let's try to solve this matrix model, like was taught to us by Brezin, Sixen, Parisi, and Zuber, the large N methods. So the idea is that you try to find, so because this action has a sum of n squared terms, when n squared becomes large, you can just try to look at the variational problem, variational critical points of V, and that gives a good estimate for the integral. And one expects something like this. Okay, so it's a sum over saddle points, and that's also nice to sort of match to gravity. Now the problem is that is what I mentioned earlier, that usually in this Brezin, Sixen, Parisi, Zuber matrix integrals, one has not just a two-particle interaction, but a one-particle interaction. So these eigenvalues want to condense somewhere, and then the two-particle repulsion due to van der Monde sort of spreads out the eigenvalues into some branch cut in the complex plane. So this is the classic thing we've learned. Here there is no local minimum. So if U is defined on a circle, you have only a two-particle interaction, then the critical distribution that you will imagine is the uniform distribution around the circle. If you calculate what the entropy of that is, you get 0. Okay, this is what was done in the old papers. But another subtlety about this matrix model is that the coupling constant is also complex. Okay, so you can see this both, as I just showed you, tau should have both a real and an imaginary part. So here, real would mean that tau is purely imaginary, but as I just showed you, the real part of tau is also important. Okay, and our idea was that, well, maybe both these problems sort of play off against each other, and we should look for complex saddle points. Okay, so this is the U plane. This is not the U plane that Greg talked about, the U just being these eigenphases I discussed. And this here is the original regime of definition of the integral. But when U becomes complex, there's another mark point called tau, which is equally natural. And if I had a periodic function, then I would imagine that instead of a uniform distribution on this cycle, I could also have a uniform distribution on this cycle, and in fact, along any lattice point. Okay, so there's an infinite family of saddles labeled by the lattice points, or I can equally well say it on the torus. The problem is now well defined on the torus, and you can ask Mn is some winding number. And what we find is that roughly this thing works. There's something of the sort that works, and the entropy of this uniform distribution of the A cycle gives you the entropy of pure radius, while the entropy of the uniform distribution of the B cycle gives you really on the nose the ADS black hole entropy. Okay, so now let me explain this a little bit. So let's start with a lemma. It says that it's the same situation that I have. You have these two particle interactions. And suppose you have a potential which is even and periodic, and tau could be a period which is complex. And you want to solve the variational equations. I've written both holomorphic and anti-holomorphic because V is not necessarily holomorphic. Okay? It's periodic. And the lemma is that the uniform distribution along the period is a solution along the line stretching between 0 and t, the solution of the variational equations. Okay, that was our intuition, and you can check this in 2 or 3 lines. The second part of the lemma is that the action of the distribution is the average value of V along this distribution. Okay, that's also easy to check in 2 or 3 lines. Now the fact that
sorry, that depends very much on the particular form of V, right? It's
not this fact. This fact is always true for
Oh,
any.
no, number one.
No, so anything, both
Any
these
V? Any V?
obeying these conditions, and S is only a two-particle condition. Okay. If it's periodic with a complex period, the only thing we use is the V is periodic and even. I can explain this to you later. What is not obvious in this setup is that because V is not holomorphic, it's not obvious why the contour deformation works. Okay. And for that, you need a separate argument. We had this in the paper at large N, and I want to make a sort of comment on this again. But sorry, this is, let me see, why is Greg confused? All I use is that it's important that the potential is purely of the two-particle type. Of course, it's not true if there's a single particle potential. That's the main point which goes into this. But if it's a sum over all two-particle pairs and it's periodic, then in the variational equation, then essentially when you sum over all pairs, you just get zero. That's roughly what goes into this. Let me continue on, and maybe you can ask me again later. Okay, now the problem is that our potential is not periodic. Okay, so it's only quasi-periodic. So in the X direction, it's completely periodic. In the Y direction, the lack of periodicity is blocked by the function theta 0, which is the Jacobi theta function divided by the Dedekind eta function. Okay, so now what do? Well, we do a deformation. So we construct a function called Q, which so Z here is Z. So I've decomposed Z along the torus directions 1 and tau, Z1 and Z2. And notice here that these things, this is a Bernoulli polynomial of Z2, and this is theta 0 to the power Z2. So this is explicitly not meromorphic. But when Z2 is 0 on the original contour of definition, Q is equal to 1 over gamma. Okay, so that's why it's a deformation. So it's the original problem we're not changing. And now this function has the following properties. The absolute value of Q is doubly periodic. Z goes to Z plus 1 and Z goes to Z plus tau. And the sort of interesting statement is that minus tau 2 is the imaginary part of tau. Tau 2 times log of the absolute value of Q is this particular Kronecker Eisenstein series. Okay, it's the imaginary part of this Kronecker Eisenstein series. Okay, so this notation I've borrowed from Zagier's paper on this, and this particular Kronecker Eisenstein series is has been studied intensively by mathematicians because it's equal to what is called the elliptic dilogarithm studied by Bloch and Wigner. Okay. For us, at the moment, the only thing I want to use is that there's an explicit Fourier expansion along both directions that's just given by this formula. I can just read it off. And therefore, you can, so once we extend the Super-Yang-Mills action as this, you just, by the lemma, you just get a family of saddles labeled by any lattice point, and the action of the saddle, which is the average value of the potential, is now very easy to calculate because the Fourier series is given to you. So the average value is again a 3-line calculation. You just use the Fourier series and read off the appropriate Fourier coefficient. Okay. So before I present the result, I want to just say one remark which is slightly parenthetical, which is to hook back to this equation. This equation that I showed you here, over here, is actually the imaginary part of a nicer equation, which is like this. Okay, which says that this Bloch-Wigner function is actually the period function. And here, so this is, so log Q minus its modular transformation on the left-hand side. Okay. And I want to say that there's actually an analogous formula for, sorry, this should have been absolute Q here. By absolute Q, replaced by the actual elliptic, the holomorphic elliptic gamma function. And this formula is some kind of a single valued version of that formula, which I'm not showing you. This is work in progress with Stavros Garoufalidis and Don Zaghir, which in turn is connected to a notion of what is called holomorphic quantum modular forms, for which I refer to you to Don's talk. Okay. So this whole thing is a bit parenthetical, but I want to say that this formula, which I've not shown you, can be used to sort of get around this and indirectly write a holomorphic argument, at least to all orders in perturbation theory. So now I want to show you the results. So the result is, by the result, I mean, I want to calculate the effective action at any saddle point, Mn. And as I said, the calculation is easy. The answer is also easy. It's just in terms of m tau plus n, it's just 2 times that plus a Dirichlet character cube divided by m tau plus n square divided by n, m. And for mn equal to 0, this is exactly the free energy of the black hole. So now we can play the following game. Say you fix yourself at some point in tau. Okay, so over here, say, and you ask of all these phases, whose real part is maximum? So which dominates? Okay, because you're looking at the contribution to the full functional integral. You find that for large values of imaginary tau, it's just the 0-1 saddle, the pure ADS, that dominates. As we go towards tau equal to 0, the black hole starts to dominate, as you can see here. And this is this other complex conjugate solution that I described. Okay, so this at least partially answers Greg's question. There is another phase, not yet about the physical interpretation, but there is this phase. Here I've cut off the imaginary tau at 0.1. But now notice that if tau goes towards the rational point, then the Mn saddle, that particular rational point, will start to dominate. If you go further down, like so, here tau goes to, imaginary tau goes to 0.01, you'll see that near every rational point, there is a new phase that is dominating, and there are these phase boundaries that you can calculate. Okay. Now, I have 5 minutes, is that right? Okay. So then I want to say, so let me just pause for any question about this. So that's the phase structure that we have. I'll just make some comments. So I want to write a formula like this. What do I mean by the symbol? So I don't have it, certainly not an exact formula. But in fact, I don't even have a classification of all saddle points. That's not the claim. What this formula means is that if tau goes near any of the rational points, then this expression gives you the complete asymptotic expansion at that point, okay, at the rational point. That's what this formula means. Now, if you take n square really going to infinity, and if there are no other saddle points, then if you're in one of these chambers, then the contribution from any other chamber goes to 0 exponentially as n square goes to infinity. And therefore, the only tau dependence remaining is the chamber dependence. Okay, so that's a comment. And all this, like, this was sort of using lots of methods and some intuition. Instead, you can just ask, okay, can I just directly study the Cardi-like asymptotics? And you can. I'll show you this in a second. I want to discuss a little bit of physics about this older paper of Greg and collaborators. I'll not do this, I'll postpone this. Sorry, there was a question by Greg, so let me just explain. Let me give you one sentence answer. The answer is that, in fact, so the prediction from our work is that there's a family of gravitational solutions. And from this old paper of yours and others, the expectation is that these might be orbifolds of the black hole. And something like that has been borne out in this very recent paper of these people. Okay, so I'm happy to discuss more about this again. Now, this is my last slide. So now if you want to be a little more rigorous, you can just say, okay, forget about these large n methods. Just go back to the Cardi-like problem, fix yourself to some rank n, and ask, can you calculate the complete perturbation expansion? And these methods that I showed you, the Euler-Maclaurin, you can actually just use that to form a complete, to develop the full asymptotics. And the surprise from that point of view is that the expansion indeed terminates at linear order. So it starts with 1 over tau square. There's a 1 over tau, there's a 1, and tau and nothing else. Okay, exactly as predicted from this other analysis. So this method has the advantage that you really have everything under control for even finite n. And the answer is that the asymptotic expansion near any rational point minus n over m looks like this. There is this function that I just showed you, the effective action. And you also have control. So one disadvantage of this large n method is that the O of one term, the imaginary part of the O of one term, you don't have control. That can be fixed here. And there's a bit of a surprise that at every rational point, you find that this number is the partition function of Chern-Simons theory of rank n and level plus or minus n on S3 quotient by Zm. Okay, so when this is 1 over m, for instance, you really get a length space. Okay, and then there is another surprise that every term on this right-hand side can be interpreted in terms of three-dimensional Chern-Simons theory. Not just the constant term, but even these divergent terms can be interpreted in terms of three-dimensional Chern-Simons theory. Okay, so I won't have time to explain that, but again, I'm happy to take questions. I want to stop now. Thank you very much for your attention.
Thank you very much, Samir. This was a very nice talk. Are there any questions?
Can you say a little bit more about the last line, please?
I think Greg raised a hand before.
Oh, okay, that's right. Yeah, Greg, please just go ahead. Yeah.
Samir, could you please explain more about the connection to Chern-Simons theory, which seems interesting and interesting?
Okay, I think this was also Shara's. So this is a physics. Sorry, let me just see where it is. There's a bunch of things. Here it is. Okay, so. Okay, so the story is as follows. So you remember, so I'm going to use physics language. To start, so you want to calculate some functional integral on S3 times S1. Okay. So the idea is you ask what happens when the circle size shrinks to 0. And you would expect, based on effective field theory, that there is some description in terms of three-dimensional theories. Now, what we do is, so how do we calculate this effective description? So you say, first you write down all possible terms that can be written down consistent with the symmetries. And that was given to us in these papers. So this was for general bosonic theories, and this was the supersymmetric analog. So, and the statement is that so there's a complete set of terms known, and all of them are essentially supersymmetric completions of some or the other Chern-Simons terms. I have to explain that a little more. When you look at this gauge theory on S3 times S1, what you find, in order to preserve supersymmetry, is that you have to turn on some kind of backgrounds to support the supersymmetry. These backgrounds can be interpreted as a rigid supergravity. Okay? So there's some gauge fields and metric in the background supergravity, as well as your dynamical fields. And the effective Chern-Simons theory and its supersymmetric completion involves both the background and the dynamical fields. Okay, that's just your theory. That's what you would do if you just did the physics correctly. So that's what we did here. There was also a parallel paper on the same day. And now you have to calculate the coefficients of these effective actions. That coefficient, in general, is not easy to calculate, but the fact that every term contains at least one Chern-Simons term means that you can use the fact that it's one loop exact and explicitly calculate a weak coupling. So what you have to do is to integrate out all the Kaluza-Klein modes. You get some infinite sum. You have to regulate that. You can do it, and what you find is you get exactly these functions that I showed you. And the story is roughly that the background terms give you the singular pieces in this asymptotic expansion. This is the sort of main new point in physics, that you can account for this 5-dimensional black hole entropy directly starting from a 3-dimensional Chern-Simons calculation. The dynamical terms gives you this constant piece. And then there's this Casimir energy because there's an issue between path integral and Hamiltonian index, and that gives you the linear piece. So everything really fits together perfectly, as you would imagine.
So I think there was one other short question maybe by Shariar.
I think it was the same, but
It was, thank you. It was the same. I wasn't looking at the participant list, so sorry, Greg. But I can ask, I mean, a question related to Greg's talk as well. And where does this R symmetry come from? So this is not manifest in a classical picture, right? It's just it's an artifact of supersymmetry, and only shows up at the quantum level. Or?
The supersymmetric n equal to 4
yeah.
Yang-Mills theory has an R symmetry. It's you can the Lagrangian. And,
so I remember you showed n equal to 2 star supersymmetry algebra. And
sorry, you're asking a question to Greg.
No, not to you. I mean anyone. But if can you just elaborate what is the origin of R symmetry? Where does it?
So the theory I'm talking about has, let's say, so you can even talk about the minimal supersymmetric theory where there is one fermion, or the one I have has 4 fermions in.
Yeah, that's it. Yeah.
And the R symmetry just rotates the 4 fermion. There's an SU4 which rotates the 4 fermions, and I've taken a U1 of that SU4.
Okay, so if it was n equal to 2, then you would have SU2. You would have
SU2 times U1, yeah. Or U2, I forget. Greg can answer this better. But yeah.
The rank of the R symmetry algebra equals the number of supercharges you have in your theory. That's
essentially.
Yeah.
Okay, so maybe this is also a good moment to end the official.
Actually, Axel, I'd like to ask one more question if I could.
Sure, go ahead.
Go to a breakout room, so I can't go to Samir's breakout room.
Yeah, I had the same problem. I wanted to be in your breakout room.
But okay, so if I could just ask that question, because I can't go to his breakout room. But you have this, so actually 2 questions, if I may. So there was an imaginary part of that effective action, which really surprised me. Of course, you add them up and you get a real answer. Imaginary part of the saddle point action.
That's right.
Yeah, what does that mean? Is that some kind of, is there an interpretation in terms of some instability?
In terms of what?
Instability?
Instability. No, I don't think so. I think all it's saying is that, so there's this infinite number of saddle points, Mn, and there are 2 of them which dominate equally. So they both have the same real part, but equal and opposite phases. So you're asking a question about the mathematics or the physics?
I guess I'm asking more a question about the general relativity.
Okay, about the physics.
That saddle point, if the imaginary point, a part of the saddle point action indicates there's some kind of instability.
That's a good question. I don't know. It could be that there is a Euclidean solution which connects these 2 actions. I don't know. I'm speculating here. That's a very good question. I don't know the answer to this. So my feeling is that there might be some instanton-like object which might interpolate.
Okay, that's pretty cool.
Yeah, but I don't know at all. This is a pure.
Okay. Yeah, I got it. So let me ask the other question quickly. So your final result, this amazing result where you get the Chern-Simons action, could you flip that? Yeah, there. Good. So the Chern-Simons partition function on lens spaces can vanish sometimes. I'm wondering what in the world that would mean. Oh, that you have to do PQ lens spaces and you're doing 1M.
Yeah, so I should.
I'm not sure. I know that Chern-Simons partition functions on lens spaces can and do vanish. And that would look kind of funny for this formula.
I agree. So let me make 2 comments. Firstly, so this is a ZM orbifold where for 1, M, it's a lens space, and otherwise it's, I don't know what to call it. I don't think it's the MN lens space. And the other comment is that, firstly, so the 1.5 comment is that I think I didn't even know about this, but The second comment is that here there is also a certain Dirichlet character which sometimes appears, which can, for 1, 0, this is 1, and for the other saddle point is -1, but sometimes it can be 0. So for instance, at tau equal to 0, the action completely vanished. So I wonder if what you're saying is related to this. Is there a condition on P and Q when it vanishes?
I don't remember the exact condition. It's in a paper of Dan Fried and Robert Gumpf,
I'll have a look at that.
where they did numerical evaluation. They did explicit evaluations of Chern-Simons partition functions for lens spaces.
I'll have a look at that.
They discovered this interesting point.
So Greg, your hand is still up. Do you have another question?
No, I'm done. I'll take my hand in.
Okay. Okay, so maybe now we can go to the breakout rooms. There will be several, 5 again, I think. And yeah, if I can ask the speakers as anticipated to go to separate rooms, that would be much appreciated. But first, let's thank Samir again for the very nice talk.
Thank you.
Thank you.
Yeah, so I just opened the 5 rooms.